early and joining us. We might have some people trickling in as the coffee kicks in. This is the tutorial for item response theory for natural language processing. Welcome, if you're all in the right place. My name is John Lawler. I'm here with Pedro Rodriguez and Jose Hernandez Oralo. We have Jal Sadak on Zoom as our fourth tutorial presenter. We've got pretty full program for this morning. We're going to introduce item response theory generally, kind of tell you about what it is, how it fits into an evaluation paradigm of natural language processing models and things like that, and then look at some specific examples, kind of give a hint of next steps and future directions, hopefully to get you all either familiar with IRT. If you're not familiar, get you interested in its applications for NLP, if you are a little more familiar with the traditional item response theory, and then, hopefully open up avenues for discussion about future work, collaboration, things like that. So that's the goal for this morning. We have a web page set up for the tutorial. It's listed here, EACL 2024 IRT.github.io. You can find all of the slides. We have the slides broken down by each section that we're going to present, but we also have a master document that you can just follow along with. We have some Jupyter notebooks up there. There's going to be some code portions of the tutorial where we show you how to implement some of this stuff in Python, specifically using the PyIRT package that Pedro and I developed. And we also have a structured reading list. So if you're looking for more information, we couldn't cram everything into 3 hours, but if you want additional references, reading lists, things like that, that's available on the website as well. And our contact information is there as well. So want to reach out to us afterwards for questions or anything like that, please feel free. Okay, so I already introduced myself and the rest of the team. We got a nice mix of folks from industry, US, Europe, and we've all been working on IRT in natural language processing, machine learning, a couple different areas. We're going to talk about them today, show you what we hope is a wide range of interesting examples and interesting applications that, like I said, kind of get you excited about possibly thinking about this for some of your future work. So in terms of the schedule, we have the welcome slides, which we're doing right now. We're going to start with general introduction to evaluation in NLP, then move into an introduction to item response theory, talk about the different types of models that fit into IRT, how they're fit, the data you use, and look at some examples both in slides and in the code. Then we'll take a 15-minute break. There's water and hopefully coffee will be outside as well. Then we'll look at a little bit more of a deep dive into specific examples of how you can use item response theory in different natural language processing problems. Another break, 15 more minutes, coffee, restrooms, things like that. And we'll wrap up with some advanced topics, some opportunities for future work, and some concluding remarks, and be out of here for 12:30. Okay. So to start, Jal Sadak is going to talk through evaluation in NLP from Zoom. So I'm going to turn it over to Jal.
Thank you, John. All right. Let me start by screen sharing. Great. Hello, everybody. I'm sorry that I can't be there in person. So I'm going to set the stage for us by starting to give a more general context about what do we evaluate in natural language processing. And so the idea behind what I'm going to show you are to really set the stage for the later components of our tutorial, which means that we're really starting to look and dig into these types of evaluations, and I'll try to sort of contextualize the larger components of evaluations in natural language processing. All right, so evaluations are at several levels. So we have evaluations which are system level evaluations. These, many of you, most of you in the room are very aware of these. So examples of system level evaluations would be machine translation systems, dialogue systems, natural language information systems, etc. Where here a system is a not just a trained model, but possibly something as full as a ChatGPT when we integrate them. Next, we have evaluations of machine learning methods. And when I talk about machine learning methods, it's different than system level evaluation in the fact that what we're trying to do is evaluate methods themselves. An example of this would be, for instance, evaluating the difference between neural network architecture types, like LSTMs and transformers. The third one may not be as obvious. So metrics, specifically things like evaluation metrics, are often evaluated, right? Before we use an evaluation metric, we want to make sure that it is consistent with whatever we're trying to evaluate. So oftentimes we're looking for correlations with human judgments. Next, an example is annotations. So human annotations or any type of annotations data, we need to care about and evaluate whether these annotations have different types of errors, right? And look at the underlying annotations and finally data. And so uh, before we use different data sets, we want to evaluate the data sets, understand things like what is the quality of the data set? Is it domain specific? Does it have undesirable components like, say, toxicity? Um, and the reason why I'm showing you this is largely because what we're going to do in this tutorial is actually cover almost every bit of what I just talked about, where you can see how item response theory is one of one type of method for you to be able to analyze and get insights into all of these components of evaluation. So digging a little bit deeper into system level evaluations, there's extrinsic task-based evaluation. So these can be just outcome measures of whatever your final true task is of the system. Then we have intrinsic evaluations, which are basically surrogate tasks. These are tasks that are closer to, let's say, maybe what the underlying model that you're training in the system is actually trained for, or some form of a surrogate task. Then we have human evaluations, automatic metrics that are evaluating systems. So A/B testing and error analysis. So I do a lot of work in dialogue systems. And what I'm trying to do here is show you a framework by Huang et al., where they talked about some challenges for dialogue systems. And to some extent, we can start by thinking about these, like there's some key large issues that we need to care about with respect to dialogue systems. But this really does generalize to other technologies too, where we have several fundamental components like, we need to worry about the semantics of the system, the consistency, the interactiveness. That ends up turning into outcome variables. So some key factors of the system that we can look at, like, does it actually manage the conversational content and context properly, and different other aspects. And these aspects can usually be judged at a outcome or survey level. So these are close to extrinsic evaluations. And then we have key technologies like named entity recognition or intent and domain classification or sentiment analysis. These types are surrogate measures which can be used for intrinsic evaluations of the systems. And once you have these sort of intrinsic evaluations, what makes sense? How do you start to judge them in order to have sort of a commonality, right? So at the top level of these factors are going to be very specific to a particular context and problem, whereas the technologies are going to be more intrinsic and should domain generalize. And so this led to the development of the common task framework and leaderboards. So what we do is we have a general agreement that this kind of competitive evaluation has very beneficial performance effects where we have multiple people competing over years to try to improve on a particular metric over a particular data set. Right. However, there's been criticisms, like, for instance, that in leaderboards, we focus too much on the numbers and not enough on the insights in terms of what drives the numbers to go up or what drives failure. So, like I said, there's a lot of different leaderboards. For instance, Superglue, Squad 2. In particular, for Squad 2, we'll touch on some of the work by Pedro on improving these leaderboards. You know, there's things like LMSys Arena Board, which are also super common and very actively looked at, right? These are great ways of trying to understand, okay, which type of language model is best, right? And in this tutorial, we'll show you about how using at the moment already like item response theory in order to integrate this method and do some different ways of seeing leaderboards that we think will be helpful in the future. So besides just leaderboards, there's also shared tasks. Here we have a common task which is given to a community, and within that common task, we try to have people submit their submissions within a short amount of time, and then we rank the submitted systems. This is an example of the machine translation system in a recent workshop on machine translation. But we have many more like Codalab and Kaggle competitions, which are all sort of shared tasks. However, leaderboards can improve, and examples of how they can improve are basically looking at asking questions with the right amount of difficulty. These questions should be discriminative in order to be able to look at and judge how well a particular type of model or system is doing. We should have minimize the ambiguity and maximize the fairness towards any model. So try to make sure that there's no particular advantage under a type of category. It should also not be overly definitive in terms of where the rankings are, and finally, flexible in terms of the type of questions that we have that can improve. They should be introspective in terms of what's going wrong in the data set that we're using for the benchmarking. Then on these benchmarks, we often have different types of metrics for figuring out how to rank systems. So the most common is obviously averaging. So you average, let's say there's a bunch of different ratings, you just average them together. Another sort of common way is to normalize them in some way. Let's say z-scoring is one example to try to find sort of equivalent classes. However, there's a bunch of different preference-based rankings. So for instance, the Bradley-Terry-Leach model, ELO ratings, which you just saw a second ago in the LMSys chatbot leaderboard, TrueSkill, which is used by Xbox, and the way that in machine translation they're doing the ranking. And then finally, item response theory, which is what we'll be talking about a lot today. Then to look at these sort of automatic metrics and human metrics, we see that there's many different types of components. For instance, there's expert judgments, where we have experts try to do ratings. There are also crowdsourced judgments for these different types of systems. And one of the things that one needs to do is worry about, okay, like how do you put these together, right? Like how do you take into account each of these individual ratings? And item response theory is going to provide a very nice way, right? Sort of framework, a mathematical framework and scaffolding about how to actually, incorporate these, um, both on the human evaluation as well as the automatic metric side. Um, Next, we have things like A/B testing. Here, it's even more obvious that we're looking at a comparative analysis, and these kind of comparative analysis really lead themselves much better, like really well to using these types of models. So we can see, is A better, is B better, is it a tie, or are they both bad? And we can incorporate the feedback, and this is exactly what's done in the LMSys using ELO ratings. In some of my work, I've looked at these using item response theory. Um, and it's actually a very, IRT fits very nicely into this framework. And, we can really think about this in this setting as trying to understand relative abilities between two systems. So in terms of error analysis, we often want to understand different types of errors. We want to investigate where the sources of these errors are and identify um, particular types of explanations for these errors. And what we're able to do with item response theory, and it's not the only method, but along with these kind of methods is actually be able to try to identify and dig in. This is a little bit what we were talking about with this desiderata of like actually having um, introspection to try to look at types and errors in uh, system evaluations or model evaluations. Okay. So sort of moving on to annotations. Um, Oftentimes when we try to evaluate annotations, we have uh, probably the most common method, which are looking at annotator agreements, also known as rater reliability, right? And there are methods that already exist, like looking at a Cohen's kappa or Krippendorff's alpha or Fleisch's kappa. There's actually a whole bunch of annotator agreement metrics. The Again, sort of looking back and trying to integrate uh, this idea about annotator agreement back into the context of item response theory, uh, we can think even about people's judgments, right, as items, uh, where what we're doing is we're able to uh, have a different type of view on the agreement that annotators have, and possibly be able to identify um, other ways of looking at these. Next, accuracy, precision slash recall, and F-score, which are very common ways of looking at agreement. Um, these are agreements between like of the annotations and the models in order to figure out whether, let's say, there's a massive disagreement in one or the other component of these evaluations. Um, what we see this as being, it's just sort of a very common way that these are used and can be used to analyze. Uh, Finally, consistency checks, which are looking at how consistent the annotations are about between a large population over time, right? So, or over the data across any sort of dimension that we can look at. And this will be, again, a way in which item response theory can help us as we can look at different items and how the ability changes based off of looking at the relationship between the items and the responses. Um, Finally, error analysis. So a lot again of annotations aren't perfect, and so we have different types of errors, and we can, later on we'll show some examples of how we can use item response theory to look at errors in the annotations of our data. Okay, so now looking at data. So like I said earlier, we want to look at data. And here we can talk about this as training data. Often we'll look at evaluation data sets. And what we're going to do is actually evaluate things like what are the quality, right, of the examples in our training data. And John will, I think, show you some of the work on his stuff about looking at the quality of individual examples in our training data and trying to understand what subset can one use. We'll also look at the difficulty, right, of this data, because sometimes when we're looking at the data for, let's say, evaluation, if something is too easy and all of the, let's say, models or systems get them right, then it's not a very useful data point. Whereas if it's overly difficult and nobody can get it right, then again, we don't actually have a good data point for assessment. And sort of being somewhere in between is a sweet spot for thinking about how to use this data. And finally, error analysis, where we can actually look at outliers in our data and try to understand, okay, what are some of the errors in the data? And as we are able to both look at the responses or the outcomes of the evaluation, as well as um, the items or data that's being used for the evaluation simultaneously, this gives us sort of a duality of insight. All right. Well, thank you again. I'm Jao Sadak. Thank you for joining us for this tutorial. And without further ado, I will hand it back to John for the introduction.
Okay. Yeah. Any questions? Should have mentioned this at the beginning, but we'll probably pause after each section for questions. And of course, during the breaks, if we have questions, we can discuss them then as well. Okay,
In the moment questions are, I think, fine.
sorry?
In the moment questions.
Yeah, sure. If you do have questions, by all means, we can ask them, yeah. Okay, so. Okay, so next, what we're going to talk about is an introduction to item response theory, right? So we'll talk a bit more about how these models are defined, what they look like, some examples, and then lead into more specific applications of item response theory in NLP. So in terms of just an introductory motivation, John did a great job there talking about these different levels of evaluation. So for a couple more examples in that vein with a little bit more detail here, if you take standard tasks in NLP, things like natural language inference and sentiment analysis, just by the nature of how the tasks are constructed, you've got a certain number of classes, right? There are entailment, contradiction, neutral classes for NLI, positive, negative, maybe neutral for sentiment analysis. But a lot of different types of data get bucketed under those classes. And when you do something like an error analysis, or you realize, okay, certain outputs are looking a little bit different than they should, you start to see that some examples within these classes are easier than others. Some examples within these classes are harder than others, right? And some are, in between, right? And there's a continuum really within this more rigid class structure. So we've got examples here that you can read from these two tasks, and we have this rough notion that some are easier than others, right? We can kind of label some as easy or as hard, but it would really be nice to have a more quantitative assessment of the, let's say, difficulty of an example with respect to the population, or with respect to, some individual's ability to answer that question correctly, or some model's ability to answer that question correctly, which we're eventually leading to. All right, and the same notion applies to these larger leaderboards or these shared tasks, right? We report things like accuracy or some overall metric on a number of tasks that then gets aggregated up into an overall leaderboard score. But typically they take all the data for a task together to calculate this one metric. There's very little consideration, if any, of instance level characteristics in how that metric is generated, and then how that rolls up to your overall score. So you could have, a model on the leaderboard that forks an existing model, makes a tiny tweak, gets one more question right in each task, and then gets a better score. But there's not a ton of difference between those models kind of in aggregate, things like that. We want to try and get a more fine-grained representation of how these models are performing based on the specific questions or examples they're labeling correctly, labeling incorrectly, so forth. So the, again, high-level motivation is that questions are different, right? So if you have, say, two NLP systems answering two different questions, or sorry, answering one question, in this case, who did the Normans team up with in Anatolia? Certain answer patterns are more responsive and informative than others, right? So if we look at the diagonal here, where both Bert and Ken answer the question correctly or answer it incorrectly, the question itself isn't very informative for us in terms of distinguishing between Bert and Ken, right? We want a case like the off diagonal, where one model answers the question correctly, the other model answers the question incorrectly. That way we can see that this question is useful in separating these two models. If you can collect a lot of data points that are informative in this way, right? They won't always be perfectly separable, but some subset of questions will separate the very good models from the pretty good models. Some subset of questions will separate the decent models from the poor models. And then, finer grained separations there based on, large enough data set, you can start to rank these models and get a notion of how their underlying ability or skill compares to other models, compares to the questions. It gives you, again, this fine-grained notion of performance. And so, right, like we said, this is where we're informed on this off diagonal. So Joe also mentioned that, annotators can feed into how this comes into play, right? Because you assume with a data set that the labels associated with particular examples are correct, but we have things like annotation errors, right? Which leads to a different kind of question, right? If you're trying to answer a question with the wrong label, the model may be answering correctly, but the label's incorrect. So you're getting this, crossed wires where the model is actually being trained on a poor signal because of the annotator error with the label. Now you also have questions maybe that are just too hard for the current state of the algorithms. You can imagine, in the human sense, asking a third or fourth grader like a 12th grade math test question. It's just too hard. They don't have the ability to answer that question. Similar idea with models. We might just have a set of tasks that are too difficult given the current capabilities of the models. And then the flip side, of course, there's some questions that are too easy, right? All of the questions in this bucket, all of the models can answer correctly. So we get the case of Bert and Ken both answering correctly. It's not informative. They're not informative examples because we're not distinguishing between models based on those responses. Where we really want to be is kind of in this sweet spot where we have these discriminative questions. They're not too hard, not too easy, and they do a nice job of separating models in terms of performance at different levels of ability or skill. Okay, so with that in mind, item response theory is a method that has been addressing these questions in the psychometrics community for a long time, and has a number of nice properties that we think can apply to NLP as well. So as I mentioned, item response theory comes from psychometrics. Psychometrics, broadly speaking, is just the study of quantitative measurement practices. They have two kind of main areas. One around building measurement instruments. So think standardized tests, right? Things like the SAT, the GRE, other standardized tests you've taken at various levels of schooling. They call these things standardized tests because the idea is even if the questions in the test change over time, as people take it again, they want different questions, but still get at the same ability. The assessment of an individual's skill is standardized across the variety of questions. So if you know that 2 questions are roughly the same difficulty, measuring the same concept, you can swap them out in different versions of the test, and then you expect that the same individual will answer those questions, the same probability of success, and you can get a score that is reflective of the individual's skill and not of the questions that are on the test. Right? So it's just kind of alternative to what you would call classical test theory, where it's just what % correct did you get? And then, it's very kind of data dependent in that sense because the specific instances drive what % you answer correctly. So this is to make it more standardized, right? It's also used, interestingly, at companies like Stitch Fix. So if you're familiar with Stitch Fix, it's like a subscription service for clothes. They'll send you a box full of shirts or jeans or T-shirts, and you keep some. And if you don't like it, you send it back. They treat each piece of clothing that they send you as a test. And if you keep the piece of clothing, then they guessed right in terms of this is something you'll like. If you send it back, then their guess was incorrect. So you can treat that as their test of how well do we know this individual's style, say. And they use some item response theory methods to better learn individuals' style preferences, better learn which clothes match with specific individuals so that they can make better recommendations because it's expensive for them to have to handle return shipping. They don't want you to just return the stuff. So they want to get it right the first time. So they use methods like this in their standardization of the clothing allocation process that they do. So the simplest model and everything that's going to be built that we're going to talk about today builds on top of this is what's known as a 1-parameter logistic model. It's also called the Rasch model. And it's defined by the equation here. So to just go through the terminology, what we're trying to estimate with this model is the probability that a particular individual called subject J answers a particular question called item I correctly, right? So PY IJ equals 1. This is the probability that that individual J answers item I correctly. That's our kind of foundational piece here. So you can see it's at the item level with respect to a specific subject. And it's a function in the 1PL case of the item's difficulty, BI, and the subject's skill or ability, theta J. Okay, so it's defined here by this equation. And then we've got a couple of examples plotted in the curve. In the 1-parameter model, difficulty basically is an x-axis offset. So if you look what we have this plot, it's called an item characteristic curve. So for a given item with a set difficulty value, a set BI, as we vary an individual's skill, theta, the probability of that individual answering the question correctly changes, right? So that's what these curves are plotting. So for an easier example, the orange example here in the plot, at a lower level of ability, you'll have a higher probability of answering the question correctly. And specifically in the 1PL model, when theta equals B, then the probability of success is 50%. So if you were to look, got this here, for this easier example, I believe B is negative 1.5. You've got this probability of success at 0.5 at the point where theta is equal to B. Now, a more difficult example in the blue curve, here I believe B is equal to 1.5. You can see we've shifted to the right on the x-axis. So now you need a higher ability, theta of around 1.5, to have a 50% chance of answering the question correctly. Okay, so when you fit these models, given enough data, you get these difficulty parameters for your items, and then you use those to estimate different subjects' abilities based on whether they do actually answer a question correct or incorrect. Then you can feed that in and estimate their ability. Now they do get like I said, more complicated. There are more parameters. First, this is the 1PL model in plate notation. So if you're familiar with plate notation, just another way to visualize what we had on the previous slide. Right, we have our observed data, which is our YIJ, and then the latent variables we're trying to learn are those difficulties. We have one difficulty for every item in capital I, and we have one ability theta J for all of our subjects in our pool, capital J. So this is, again, just functionally equivalent to this. We'll see plate notation when we jump into the code. So I wanted to introduce it here so everybody has seen it before we get there. Now, like I said, there are other examples. Here we have what's called a 2-parameter logistic model, 2PL model. We've added another parameter, AI. It's another item level parameter, right? So it's indexed by I, and this is what we call discriminability. So now this is a representation of how well a particular item can discriminate between two models that are close in ability. So, and what that translates to in the item characteristic curves is the slope of your item characteristic curve. So if you have an item that's highly discriminative with a large AI, you'll have a steeper slope, like in this blue example. So at a more narrow range of ability, the jump in probability is larger. So if you move from maybe theta equals 0 to theta equals 1, the probability of answering the blue item correctly jumps much more than it does for the orange item, right? The orange item has a smaller discriminability value, a flatter slope. So the probability increases more gradually of answering it correctly, which means this item is not as discriminative. It'll do a decent job separating the very low ability individuals from the high ability individuals, but not as much if you're in a narrower range of ability. In the extreme, if you have, an infinite discriminability parameter, then that item will exactly note the point where an individual moves from not being able to answer the question correctly to answering the question correctly. You'll just have a straight line from 0, then it'll jump to 1. We rarely see that in practice, but just it's helpful sometimes to think about that as it's basically a jump point from incorrect answer to correct answer. And then we have, real valued slopes that we typically see. Another example is what's known as the 3PL model, 3-parameter logistic. So now, as well as difficulty and discriminability, we add what's called a guessing parameter, or sometimes a pseudo guessing parameter. If you notice in the 2PL model and the 1PL model, the range of your Y value is 0 to 1, right? There are some questions where an individual, at an infinitely low level of ability has 0% chance of answering correctly, and infinitely high level has, probability of 1 answering correctly. With the guessing parameter, we assume that there are some questions where even if ability is very low, there's some, likelihood that they'll answer the question correctly because the question has a nature that makes it easy to guess. So you can imagine an example where, multiple choice test where the question is written in a way where even if you don't know the answer, you kind of have some hints, and if you guess, you have some positive probability of answering that question correctly. So that's represented by our CI, by our guessing parameter. And as you vary that, the lower asymptote of this curve changes. So for the orange curve, in this case, we've got a lower guessing parameter. And what that means is there's less likely that at very low levels of ability, someone still has some non-zero probability of answering the question correctly. The blue question, higher guessing parameter. At those low level of abilities, it's a lower asymptote. So when you're thinking about building a test, right, you don't want questions with very high guessing parameters because they're not actually then going to be that discriminative, because even at very low levels of ability, the probability of answering a question correctly is still high, and you want it to be low at those low levels of ability. And lastly, there's another model called a feasibility model, where it's basically taking the inverse of the guessing idea. There might be some questions where even at very high levels of ability, the model or the subject, whether it's a human or a model, does not have probability 1 of answering the question correctly. So these are typically associated with things like annotation errors, right? If you've got a question where the label is wrong, even at a high level of ability, the model is not going to label it correctly. So this is, again, just another way of formulating these models. It all comes down to how these item characteristic curves are drawn. You typically want your upper asymptote to be very close to 1, lower asymptote very close to 0. So your feasibility parameter should be small. Your guessing parameter should be small. And that way you have a curve that accurately represents the full range of performance for these different subjects given these different items. Okay, any questions on the different models? I guess we can pause here real quick. Okay, so how do we get these parameters, right? How do we learn these ABCs, these thetas? What we do is we take a variational inference approach. There's a number of different ways to do it, but as we'll see a little bit later in the slides, given the constraints in terms of the size of the data sets we want to use this for, think about your NLP data sets, your machine learning data sets, they're orders of magnitudes larger than a standardized test a human could take, right? Try and sit somebody down and have them even do MNIST in one sitting, right? It's not going to happen. So we realized pretty early on that we needed a variational inference approach just to handle capacity. So what we do is we define our model as we've seen, in the past few slides, And from our collection of items that have been responded correctly or incorrectly, so it's a binary data set, either 1 if it's correct, 0 if it's not, for our subjects, we can create this likelihood here across all of our items and all of our subjects. And then we define what's called a variational distribution or guide distribution. It's called a guide in the code, more traditionally called a variational distribution, that approximates those model parameters. And then we use variational inference model fitting methods to minimize the elbow for the difference between the guide and the model. Right, so we use Pyro to do this under the hood for our PyIRT package, but there's a number of software packages that handle variational inference. The idea is you want to get your guide as close to your model as possible. Once that's done, then you have your learned item parameters, your learned subject parameters, and you can estimate the probability for any subject item pair of that individual answering that item correctly. Okay, so if there are any questions, we're going to jump to one of the Jupyter notebooks. Pedro's going to walk us through how you can define some of what we've just seen in the slides in Python to actually fit an IRT model and look at some of the parameters that come out.
Cool. So this is on the webpage if you want to follow along. So I'm going to walk through the notebook, and we've designed the notebooks for this tutorial in a couple different ways. So this is meant to show kind of more under the hood what's going on. You don't need to know everything that's here because we built a software package to hide some of this away. But we figured it'd be helpful to unhide some of this at least momentarily. Yes. Is that big enough? Cool. So we're going to make some basic assumptions, and we'll repeat these assumptions later as we return slides. If you miss these, it's fine. It's useful when trying to talk about IRT to have a generative story for your data in mind and in general Bayesian models. So this is, if you know about topic models, it's kind of a similar idea there. So we're going to suppose that in our use case, we have 10 subjects, and I picked 10 just to keep the numbers small so we can actually see what's going on. And we're going to also assume that we have some items or essentially test questions that has difficulty that's randomly drawn. We'll also assume that there is some annotation error in creating these examples. So say at a rate of 90%, the item is valid, and at 10% it's not. And that's going to play into how we generate responses. So for example, if an item is valid, then we'll say that, well, its probability of an item and a subject having a correct response is going to be determined by the IRT equation that John just talked about. If not, we're going to flip a fair coin. And that basically means that the ability of the model does not matter at all. So it's a bad question. So perusing over code that kind of shows up as creating this list of items and list of subjects. And here we're just going to set that the minimum difficulty and max difficulty is -4 to 4, and make some very simple assumptions that this difficulty is drawn at random uniform and skill is also random uniform. This is not how the real world works, but we know what the data is. We know where the data is coming from, which is helpful. Then we're going to export this data to PyIRT format. And this highlights one of the interesting things about IRT. So this will be a JSON lines formatted file, and each line will be essentially the data for one subject. And one of these dictionary entries is responses. And we made this a dictionary because you don't actually need all the responses for every model. So in John's example of the SAT or GRE, typically one student will not take all of the questions possible to be asked. So you might only have responses for 10 or 100 or 1,000 questions. In NLP, that comes up more so now than when we had originally proposed this tutorial with the rise of generative AI, that before we could very easily say, we're going to evaluate all the questions in squad. It's fine. It's not a problem. But now we have responses for models and like, well, we need humans to annotate all of these, but that's expensive. We don't want to annotate all of them. So this matrix does not need to be complete in general or when using PyIRT. So this part, I'm going to say this model that we're going to train right now, or that I trained before and I saved the notebook, is a 1PL model. So the very simple model, we just have difficulty and ability. And then we're going to go and update that model to be slightly more complicated with discriminability, which is how I'm going to kind of tear into the code a little bit. So for now, we're just going to say we train this model using just the PyIRT training code here. And what I want to convince you of briefly is that the model is actually learning what we want it to learn. In this case, I've ordered all the 10 subjects that we have by their real skill, the one that our simulation created at the top of the notebook. And then paired along with it showed the skill that IRT inferred for that particular subject. And these skills roughly line up, which also line up with just computing simple accuracy over that item test set. So hopefully this convinces you the package actually works. And since we know how the data was generated, we know that it's correct. There are, in this example, about 1,000 items. So it's like too many to show on one screen easily. So I've just taken a subsample of 20 of them and compared here the simulation-based difficulty to the difficulty that IRT inferred, and it's not a perfect lineup, but it looks roughly correct. And that's all that I'm trying to convince you of, that the package and the method generally works. So now we're going to dig into some of the code. So in variational inference, we have two important things. We have a model, and that's representing our generative story. So this is our probabilistic story for how this data came to be. And the guide, which in variational inference is the variational distribution that has variational parameters. And these two are relatively closely paired. I don't know how deep I want to get into that, but for the purpose of the code, what we really need is to define the model in terms of distributions and the guide in terms of distributions and parameters. So I'm going to skip down a little bit and I'll go back up. But in terms of code, what we really care about, I'm going to walk this back a little bit, is I'm going to start with this. So in Pyro, you define a model, and this is our model function, model hierarchical. And there are a bunch of things that are defined here, which I'm going to skip for the moment. The thing we care about here is that we observe some data. The observed data is that XY matrix. And that observed data is just the response patterns for a given item and subject. And from there, we're saying that this is sampled according to a Bernoulli distribution. So flip a coin based on these logits. And these logits match the IRT equation that John was talking about. And if we look at where these things are coming from, these are also defined as distributions themselves. So for example, if I look at ability, where is ability? Am I blind? Look at theta instead. To ability. So ability here, which is theta, we're basically assuming that this is coming from a normal distribution with some parameters. And these parameters are just suppositions because it's a Bayesian model that could be correct or not. The thing that's paired with this is a similar Pyro guide. And this is mostly mirroring the top. From here, the main point I kind of want to make is that this is all hidden in the PyIRT package, but adding code to this is not that complicated. I don't know if I'm doing a good job of convincing you of that. But I'm going to return to the top so we can continue going through the notebook. Or the here. So all of this is resulting in this model. Which is the plate notation that John was talking about. Where we have the observed data, which is coming from the IRT equation, and that's based on the betas, the gammas, and the thetas, which are the difficulty, discriminability, and skill. And using this model, then we can train again. And the main difference between the model that we trained initially was that this introduces discriminability. Flip back to the slides, John.
Yeah. Any questions on that, on the walkthrough?
Walk through it a little fast. We weren't sure how hacky codey we're going to get. But this is something we're happy to talk more about. I don't know if there's a lot of value in, not hacking and coding it.
One thing to note is that the raw Jupyter notebook is on the tutorial site. So if you want to download it and actually rerun these cells yourself and play around with the model guide definitions, you can certainly do that as well. Right?
Sorry, can I ask another question?
Yeah.
Yeah, maybe just a bit, but I was wondering, how do you actually define the priors here? Like, how do you decide on these? So because I saw you go that, yeah, priors equals,
Yeah, maybe we'll talk about one of these choices, which we'll talk about also a little bit later. To some degree, choosing the priors. To some degree, choosing the priors is I don't want to say intuition, but let's use discriminability as one example. So we can assume that discriminability, there's two ways we could say. We could say discriminability could be any value sampled from a standard normal distribution. That has some implications in that the discriminability could be positive or negative. So that tells me that in the IRT equation, there could be examples that where if the model gets more skilled, it's more likely to get the answer wrong. So where could that be helpful? That could be helpful if we have a data set, for example, where we have a strong suspicion where there are examples that have bad labels. So if I have a question like, who is the president of the US in a certain year, and that answer is wrong, then all the models who guess that answer correctly will get punished for answering it correctly. But if that's not something that I think is happening in my data, then I can say, well, instead, we'll say that discriminability is sampled, or log discriminability is sampled from a normal distribution, or discriminability is sampled from a log normal distribution. And that's basically saying, I think there are some examples which will be more useful than others, but I do not have any cases where having where the model being more skilled results in it getting a lower accuracy. So that's kind of one example where you might choose one prior over a different prior. But in general, it's a mix of kind of part of that intuition and does the model actually fit or not?
Great, thanks.
Just in the original, many of the American populations, they assume abilities to be normal as basically. So they assume that zero abilities is some kind of average. And you have some intuition about some models having more than something. You can start with those priors. I think that's why we get something like -7 capability or +3, because it's your choice, but it depends on the incremental and the use, depending on on your package, what kind of distribution works better. But normal distribution is one of the five more choices.
Okay, great.
I have a question. For example, if you have animals, but you don't know the correct label, if there's some additional variable that you can add. So for example, if so you can say, well, the correct answer is just the minority of false. You can also say, well, the correct answer is yeah, for example, this is more certainty. So it's preferable to be pretty good correctly. If there's some kind of a way, if you do the product, if you don't have the label, but you want to infer it based on output of animal.
Yeah, so the base IRT formulation is really around testing and assessment. So the assumption is you have those labels. But the probabilistic models can be designed in a way where that's either like latent or like semi-supervised, or some labels but not others. You can just adjust your probabilistic model that way. So that would require kind of defining a new model that you just walk through, but it's just a different probabilistic formulation. Yeah. And the traditional IRT assumes you know the right answer, because usually it's like test makers who are writing the question, they write the answer. So the jump to more of a like unsupervised or like semi-supervised scenario. You just have to make some tweaks.
Yeah, because you can, for example, infer the quality of humans.
Right, exactly.
Versus a computer, because human annotators are
Right.
Yeah, that might be.
Yeah, there was some work, I think you tackled, Dirk Hovey and colleagues did like a probabilistic model of annotation, it was called. They get some of that, because different individuals will have different skills for annotating. You don't know what the right answer is, and they do a nice job of breaking them down.
Nice. Okay, perhaps we
Yeah, we can have more on that, yeah, sure, yeah.
So am I right in order to use this, you need to be assessing multiple models where you can kind of assume that they're relatively independent from one another. So like for example, in a situation where you're trying to do hyperparameter tuning wouldn't probably be a very very way of doing it, because you then can't really presume that like this model
Yeah.
has equal 0.3.
It's a gray area, I think, because so technically the IRT assumptions are something like the subjects are relatively independent, but in machine learning or in like SAT or standardized testing, that's much more true, in that you can imagine students being drawn from a normal distribution. That may be a problematic model of the world, but it's kind of what's assumed. But for example, in a lot of the work that I've done on like leaderboard stuff, that's technically, yes, they're different models, but they're all like, well, it's BERT, and then this variation of BERT, and then this variation on variation of BERT. So I haven't tried it with hyperparameters. I don't know.
A little bit, yeah. We'll talk a little bit about it in the slides again. But yeah, we relaxed that assumption, and it's the same assumption typically applies with items. You kind of assume item independence, but think about any data set that we're going to evaluate. Even sentiment analysis, like there's a lot of overlap, or question answering, there might be a lot of overlap. So in relaxing those assumptions, you know, we still are able to fit these models, but we're not as rigid as like the standardized tests. So. But it's, you know, different use cases of the assumptions kind of have got a little bit of.
Yeah. And I think some of it kind of, some of the variation kind of not guarantees, but estimates like might not be right. But if what you're interested in is like getting some insight from the parameters, you could still get insight from the parameters, even if say maybe the assumption that like the difference between a one skill level and next skill level is supposed to be a certain amount of z-score probability. That might not be true if the assumptions aren't true.
And a little bit of the correlation between models and like their independence. So I played around with in your experience, do you think it makes sense to throw a couple of bad models, just like if most of your models, let's say transformers with like relatively comparable performance, do you think it makes sense to throw a couple of like standard APMs just to have a bad model in the mix?
I haven't purposefully done this, but the squad leaderboard definitely contains, which is a lot of the data that I worked with, definitely contains some models which are not very good. I think we left most of them in, but there were some truly bad ones that we left out.
I've done that as well. We use the optimal model and the testing a model, and then we further parameters. These populations, you have a full population of models that not going to affect your estimation at all. And you always have two extremes. Yeah, it goes well, so it's.
I guess it depends on what you're getting, like if you're doing litter reporting, then you just do the model, reporting. Like the work that I was trying to get properties of the data. In which case you basically choose which models to use to kind of generate those things that ended up like basically intentionally choosing models specific to another ones to kind of get a.
Yeah, especially around the data characteristics, you want a lot of variety there, as much as you can get.
And I got mixed results, but
Yeah.
I guess models, some of them is very nice. As in, for practitioners, we use the fix the data and you can then actually create the survey, actually test design. These questions are very different. But if I didn't have a bad model, then I could doing my test only to that good. And so there's a trade-off there for a practitioner. We have guidelines on how to operate with the creating too much of your good models versus like test design in general at the full spectrum representative.
Yeah, there's a risk there, especially as progress gets like more and more incremental. Right? Because once you get to a point where it's really maybe 20% of your data set that's relevant and discriminating between the top performers and the very top performers, then all those easy items are going to be potentially discarded to build a hard data test set. Right? Like, and there's some examples of that, like the hard SNLI, there's just the specific difficult ones. But you run the risk of then overfitting to the hard data, right? So you always want to come with at least a couple. And the nice thing about something like IRT is you don't need 50,000 examples where maybe 10,000 are easy, 20,000 are in the middle, and the rest are hard. You have enough where you've got a few at different levels of, let's just say, difficulty, or your various parameters. Then when you do your model ability scoring, you can fit that model with just a handful given those parameters, and then whether they got it right or wrong, to at least get close. So yeah, you still want to keep some, and it's a little bit of test design, which ones are retained, because maybe you have two with the same difficulty, one's more discriminative than the other. You might want actually in that case like a little bit lower discriminability because you're talking about the upper degrees, so you want some coverage here. But yeah, that's very much a test design question, but you can do it efficiently.
So there's one paper I'll mention at the end, where the idea basically is, can I have a human in the loop on generating questions and have a pre-estimate of how difficult the question is going to be, so that you can control the difficulty a little bit more. So that kind of thing is definitely like an open direction, I think.
So I noticed in this simulated example where you have actually different errors when you estimate the ability of each individual model. Does that have some implications if you're comparing models performance or ability actual case where you don't know like the true
Is this you're talking about like this notebook or the section 3 notebook?
just
This year.
I missed trying to figure out what you're asking.
oh like
Sorry.
you see the estimate of the real scale and the inferred scale, you have some stars, right? I mean, that's okay, that's unavoidable, but it's larger for some model / individual.
Yeah, and I guess some of this is that the scale on these is not the same. I'm mainly looking at the rank of these, because the left side is like this random uniform -4 to 4, and the right side is parameters that are intended to be on a standard normal distribution.
One other thing to note is tracking model training, we just use negative line weapons. You can see how close the latent parameters fit the observed data, the correct answers. You get a sense of how well those latent parameters map. But skill and ability are, we don't have reference points. That's why we use this.
The other thing that's probably worth mentioning here is you can, with accuracy, you're looking at just accuracy differences, but with skill, particularly when you assume like a normal distribution, you can use these scores on the parameters themselves to get a sense for like at a given skill level, plus or minus a different skill level, what's like the likelihood of falling in that range and get a better confidence intervals and whatnot.
Right, keep going. Cool, thanks for the questions.
Yeah, the questions make it much more fun.
Yeah, exactly. Okay, so back to the slides then. So now hopefully, we're more familiar with the IRT formulation. We've seen the example from the notebook about how this actually translates into learning these parameters. Next, we're going to take a look at some just kind of high level examples to motivate the third session. And then we'll jump back into the code for the kind of command line version of the I wanted to work without getting too deep version of things. So we saw these examples before, right? We knew that certain questions were easier than others, but now if we collect, in this case, it was actually human data. We went to Mechanical Turk and had, I believe 1,000 annotators label each of these items and then use those responses based on, against the gold standard that we had from the original SNLI dataset or SSTB, the Stanford Sentiment Tree Bank. We could fit these parameters. So now we know for that entailment example that we thought was pretty easy from that early motivation slide, the difficulty is actually very low. And recall, low difficulty means you're shifting that item characteristic curve to the left. So at a lower level of ability, you've got a higher probability of an individual answering the question correctly. So again, you kind of look at the first one, a little girl eating a sucker, a child eating a candy. It's entailment and it's an easy one to spot. Contrast that with the next one. Right now, we've got an example that's contradiction. In the raw data, we had a lot of variety from the annotators. Some got it right, some got it wrong. And that translates with all the response patterns fed into our model fitting process, a higher difficulty. This one was just harder for individuals to label correctly. And we see the difficulty 0.5. So now you have to have basically above average ability. Remember, ability is kind of normally distributed to have a 50% chance of answering this question correctly in that human population. We'll eventually transport this over to models, but we started with the humans just for kind of a validation perspective. And then some more examples. Again, the sentiment analysis ones I think are funner because it's really easy to see the super negative example as very easy, right? That first one, here we've got this here, right? Not too many people are going to say, oh, that's a positive review, right? So again, very low difficulty parameter. But this one here in the data set, it's labeled as negative, which again is critical because we're assuming these gold standard labels are correct. We'll see when that's not the case later on, but it's a little bit more on the fence, right? It gets the job done, sleepy afternoon rental. It was labeled negative, but on the fence. So it's much harder. Some people pick negative, some people pick positive. And that then reflects the fact that more people got this one wrong than say the first one. So we now have a kind of quantifiable way to distinguish between entities in a particular class using these IRT learned parameters. Now, if we keep going with that, we can turn these into test sets, right? So if you have a data set where you can, assume certain examples are easier or harder a priori, and in this case, what we did was for natural language inference in SNLI, there's a validation portion of the training set where they got multiple annotations. So SNLI is decent sized data set, but for a subset, instead of just getting 1 or 2 annotators or 3 annotators, they got 5 annotators as like a quality control check. And there was some variation in those checks. Some annotators, in some cases, 5 out of 5 annotators agreed. We considered those easier, just as like a bucket. And in some cases, only 4 out of the 5 annotators agreed. So we considered those harder. In the original paper, I think they discarded anything with lower than 4 out of 5 annotator agreement on the quality check, but those were also very rare. So we can take those items, learn the difficulty parameters of them, and then give the test that is generated as a result of that IRT model fitting to, I think in this case, it was an LSTM model at the time. And what we learned is a couple interesting things. So first, I want to just show you the test accuracy, right? So the first kind of thing to note is what we thought were easier, right? So raw accuracy on these test sets, right? We see 96%, 87%, 80, 88%, excuse me. And then in the harder test set, the raw accuracy is lower. So 78%, 83%. So they, roughly speaking, are harder. But now let's look at the learned ability, right? So for entailment in particular, with this test accuracy of 96.5%, the ability is actually below 0. Now, why is that? It's because everybody's answering all these questions correctly, right? These easier questions all have lower difficulties. So when you give that test set to a model, if it's also answering most of the questions correctly, then it's going to basically be in the middle of the pack with regards to all the humans who have evaluated this test set, all the human data that was used to fit these model parameters. Contrast that then with the lower accuracy here, 78% for those hard contradiction examples. Even though test accuracy is lower, now we've got a much higher ability score because this test is harder for everybody. So by answering more questions right, even if it's not raw value as high of an accuracy, you're getting a higher ability score given the nature of the questions. So this goes back to what we said earlier about this notion of standardized tests. You want ability to be somewhat independent of the specific questions that are asked. So even if you get 96% accuracy, your ability should be representative of your skill and not the fact that you're able to answer a bunch of easy questions correctly. Now, a couple key things with this that are important to note with regards to IRT. The test set construction matters. We were talking about that a little bit earlier, but if you only give questions, if you only have a test set of easy questions, then your range in which you can discriminate between abilities is relatively limited to that easy range, right? Because if your maximum difficulty of a question is -1, you don't have any mechanism of deciding if somebody's ability is like 0 or 1 or 2 or 3. So you want a variety of test questions, right? You want some easy ones, some hard ones, some middle ones in the same test set. So you can get all of these collected, right? What we're illustrating here is that you don't have a correlation between accuracy and ability, but ideally these would all be in, well, what I'll say is 3 test sets, but I'll say why in a minute. So that you have a comprehensive assessment of a particular skill across levels of difficulty. Now, the second thing is ability is assumed to be unidimensional, and it's assumed to be with regards to a particular skill, right? So if we look at the ability score here, this ability score is with respect to someone's ability to identify that this is an example of entailment, yes or no. The next one is for the ability to identify something as an example of contradiction, yes or no, right? So if you have a test that's covering multiple dimensions, you want to make sure that you have questions that are assessing those dimensions at those different levels of difficulty as well. And we'll talk towards the end about multidimensional IRT and some of the constraints and difficulties and challenges and opportunities that presents. But you want to make sure that you're kind of clear on what ability represents in terms of the thing you're assessing, and then have coverage in terms of difficulty across your typical range. Again, we're assuming a standard normal. So -3.3, -4.4 is what we typically would use. Okay, so that example, like I said, it was calculated using data we collected from the crowd, but getting response pattern data from humans is expensive if you're not a standardized testing company that gives the SAT. So we already mentioned this a little bit, but can we use ensembles of models to do this response pattern collection instead of humans? And if we can, does it make sense? Are we going to get data that's valid? Are we going to get data that's actually giving us response patterns that lead to fitting appropriate and reasonable and interpretable IRT models? Okay, so just talk a little bit about some things we've tried in terms of making this happen. This is very much open for research, what the right way to collect your ensemble of models is, whether it's hyperparameter tuning or model architecture selection. This to me is kind of a big open question, so it's worth for discussion or suggestions, or want to talk more about it afterwards for sure. So let's think about the GRE, a traditional kind of item response theory test set creation process. You start with a question bank, right? You've got some collection of questions that have been written by experts. If it's a medical licensing exam, you'll have a number of doctors in that field who write these questions. They take, they're very careful about it, very precise. They write the answers, they validate the questions to make sure that they're actually assessing the thing that they want to assess. They're not giving the answer away with poor multiple choice alternatives, things like that. You collect a large number of those, and then you go out to the populations of doctors or med students, whoever's taking your test, and give the test. You'll give enough questions that you get responses for kind of as many questions in your questions bank as you can, while having enough overlap that you don't have subject A taking a unique test and subject B taking a different unique test with no question overlap. You need to make sure that subjects A and B are at least taking a proportion of the questions together so that you can link your parameters when you're fitting your model. Then you fit your IRT model, you get your learned parameters, your difficulty, your ability, your discriminability, and you inspect. You can do something like a factor analysis to see if the learned parameters load on the factors that you expect, given the test and given the content. You can look for things like negative discriminability, where those questions would be removed because they're not doing what you expect. The higher ability individuals are getting it wrong. And this process is very iterative. You'll have psychometricians go through multiple rounds of item removal, model refitting, checking the goodness of fit, until they get to their final test set that has, like I was saying, coverage across levels of difficulty and a good fit for estimating a particular test taker's level of ability. Like we said, collecting the question bank on the, or collecting the response patterns on the machine learning model side is trickier. So what we want to do is, instead of our question bank, we assume we have some training set or some data set that has been annotated. We have our known gold labels. And then the green box here, this is where we do something, let's say, to inject variety into the system of response pattern collection. So what we proposed originally back in 2019 was to manipulate the data set and fix the model architecture. So instead of collecting a number of different models and running them through the same data set, we took a subset of training data and injected noise, flipped labels, manipulated the inputs to make the data messier, and then make the training noisier so that the model would perform more poorly, right? So we've got this like a set architecture in the case we used one LSTM and then one another base architecture. And we took those and gave them different data sets to generate our response patterns. Now, alternatively, you can fix the data set and manipulate hyperparameters, manipulate model architectures. This is that kind of open question that I mentioned. This is where I think there's a lot of room to explore, or you can collect from a leaderboard, right? But ultimately what you get is that collection of response patterns that you can then fit your IRT model with. And this is a lot cheaper than, going for human annotations. You can just run this in as long as it takes to, train those models. And you get a much larger collection of data, again, because these models can label tens of thousands, hundreds of thousands of examples, which a human sitting down on MTurk would not be able to do for us. So first thing we wanted to look at really was how well those learned parameters correlate between our human response pattern data set that we used for those test sets a few slides ago, and then what we learned using our artificial crowd, our machine learning ensemble. And the takeaway is we've got decent correlation, right? The easy questions are easy for humans and machines. The hard questions are hard for humans and machines. There is variation, of course, and we'll see some examples of where that was the case. They're actually kind of interesting. But our goal here was kind of a sanity check to say, okay, are we learning these parameters in a way that makes sense? So this was for natural language inference, similar result for the sentiment analysis task. And again, we've got our two models here. One was an LSTM and one was a neural semantic encoder, which we had been working on at the time. The other thing to look at was the difficulty distribution, right? So we mentioned that we make this assumption that ability is normally distributed, difficulty is normally distributed. So with our IRT parameters that we learned from our machine data, do we see that kind of normal-ish distribution in difficulty? And the short answer is yes. For our two data sets, they're roughly normally distributed. You can see the sentiment analysis data set, SSTB, is a little easier than SNLI because we've got the kind of the peak of that distribution shifted left. So overall, that task was you could say that task is a little easier than SNLI based on the distribution of difficulties of the items in there. Okay, so just as a kind of preview for what we'll do in section 3, these are just a couple of examples of how you get to those model parameters, right? So at this point, we can hopefully say that we've got a method for learning these latent variables for instance level data, and we kind of want to do something with them, right? So we now have this. We can show that it's appropriate way to learn these values, and we want to use them. So one example would be, like we said, to apply this to something like a leaderboard, right, where you have all these models submitting all the predictions. We can collect that data, fit an IRT model, and then analyze the outputs, try and see, okay, what kind of questions are in squad 2, both from difficulty, discriminability, and then that feasibility parameter we also mentioned. But then also, are we ranking the models appropriately, or are there more efficient ways to rank our models? So like I said, we're going to dig into this in the next section, but just as a kind of preview, we can see the item parameters give us pockets of questions, right? So squad 2 has a very large number of questions in it. Some are easy, some are hard if you go left to right. Some are highly discriminative. Some have negative discriminability, which again, we mentioned correlates with that annotation error. So these are questions that are maybe, candidates for removal, right? Or at least candidates for review. You want to look and see, all right, are these questions, do they have the right answer? And then we've got these feasibility values as well. So we want, like I said before, high feasibility so that they're answerable. So again, we'll dig into this, but again, just to show you one thing that could come out of this, you get this kind of data analysis of your test set based on all the data that's coming in when you're doing your scoring. And then another thing we wanted to look at was in terms of ranking performance, can we efficiently rank models without needing a 10,000 example dev set or 10,000 example test set? If we're careful about test design, picking examples at various level of ability, discriminability, we actually can do really well in terms of rank correlation with a full test set. And again, we'll dig into the details a little bit later. Okay, so the last thing I want to talk about in this section here is any questions from the last few slides? All right, so I want to officially introduce the PyIRT package. Pedro and I developed this package to answer a couple questions. One, we wanted to work with IRT in Python. Most of the IRT work and packages are in R. It's psychometrician heavy, social science heavy, so it all kind of is in R. We were looking for a solution in Python that could scale, right? So if you look at some of the traditional IRT packages, they'll be fit via like an EM algorithm or give sampling or something that doesn't scale well to the huge number of models and subjects that we want to work with in this NLP context. So as we saw already, we've got a particular input format where we have our subjects that can be ID'd by strings, and it gets mapped under the hood. And then their responses to questions, right? So question 1, 2, 3, 4. Again, this doesn't have to be complete. If an individual only answers a subset of questions, you just include that subset and it'll be part of the model fitting process. And then with the command line, you can run PyIRT train, specify the type of model you want to train, 1PL, 2PL, 3PL. If you define your own model in the package, you can just plug that in, you assign it a keyword, plug it in here, give it your data, and then what it gives you out is your learned abilities for the subjects, the learned difficulties for the items, because this is a 1PL model, and then a mapping, right? Which item is associated with which item ID, which subject is associated with each subject ID. And then this is kind of the building block for your downstream application. You take this data and then analyze your squad data set or whatever other piece of data you're looking to work with. So, we've evaluated the package. It's certainly faster than the options in R. We compared with MIRT in R. And once you get past a certain number of items in particular and subjects, the runtime with MERT either gets just very high or it's not able to do the computation because it requires building out the full matrix to do your EM calculations. So the variational inference setup that we've designed in PyIRT lets you do this efficiently. And then it's also built on top of Pyro, which is able to work with GPUs. So if you have a GPU, you just get an extra speed up comparing the red with the orange as well at those high levels. So PyIRT, it's on PyPy. You can pip install it. The latest version is 0.6. We're actively working on it. I wanted to shout out a few other contributors who have helped us with some bug fixes and some plugging in of additional bits of code. So if you want to contribute, if you have feature suggestions, if you want to play around with it, by all means, let us know. And then I think now we're going to look at it. Yeah, we're going to look at it at a more kind of closed form solution than what we did in the last notebook. We're going to assume that you have your data, you want to fit your model, you want to use the package. So we're going to jump to that now, unless there are other questions. Okay. So this collab file is also on the welcome page. So this is going to be IPyNB Notebook 2. We're looking at the HTML export. If you want to download it and run it yourself, you can click this link. If you want to run this one in Google Colab, it's up on Colab. Click that link, make your own copy, save it to your drive. and it'll, it worked when I tested it. That's the best, that's the best guarantee I can give. If it doesn't work, of course, let us know, but I can't say it will work because then it won't work. So it worked when I tested it this morning. Hopefully it still works. Okay, so like I said, in this walkthrough, we're going to assume you don't want to build your own model. You want to use this off the shelf to get those parameters and feed them into your use case, your downstream use case. So we need data that looks, like our PyIRT format. Pedro showed you how you can do that, how you can create it in Python. I'm going to show a different way of like translating it from an existing data set. If you're going to do this on your machine, here's just one way to set up your environment in terms of installing prerequisites and things like that. Once that's set up, you can just pip install pandas pyro, which is under the hood, and then PyIRT. It needs some dependencies, it needs torch in the back end, things like that. So this can take a minute. But when that's done, you should be ready to go. Now, the data set we're going to use here is a collection of response patterns from COLA, which is part of the GLUE leaderboard. So I've got a copy of the response pattern saved up on the web. You can just download it here, read it in, and we can see the format here. So the format that, I typically save stuff in before converting it to PyIRT is model ID, item ID, and response. So this is an example where we use that artificial crowd construction technique where we manipulated the training data based on injecting some amount of noise. So the models are defined by the percentage of the data set that was modified. We kept it below 50% because if we went above 50%, we're basically learning a new task. So we figured between 0 and 50% was reasonable to get pretty good models, pretty bad models, and everything in between. Then all the item IDs, and then the responses, whether it's 1 or 0, to label it correctly or not. Okay, so what we want to do is just take this, convert it into the dictionary that we need. It's just a simple loop to build out that dictionary of subject IDs and then your responses. And then you're going to write that to the JSON lines file so that you can access it when you call PyIRT. All right, so here's the command that we saw in the slides, right? PyIRT train, we're going to train a 1-parameter model. Here's our input, and then here's our output. We want to save it to this cola1pl folder where we're going to get our output files that we can examine. The training doesn't convert well to HTML, so I'm just going to jump down to the end here, but I do want to show you what I guess the end of it looks like. So during training, we log passes through the data where we log our training epochs. We log our loss. We track our best loss in terms of saving the parameters associated with our best loss. And then we also decay the learning rate so that as we move our way down that slope, we can make finer grained updates as we go. As we're tracking here, the thing to keep in mind is that we eventually kind of start to converge on a loss. We see here the decreases in loss get smaller and smaller. We're getting to a point where we're close to convergence. The curve is kind of flattening off. In the package, you're able to adjust the number of training epochs, adjust the starting learning rate. It's very configurable in terms of hyperparameter tuning to get a good training run or to get results that you would expect. It's going to vary by data set size, whether you're doing a 1PL or a 3PL model. So you have to plot those loss curves and have a look at the data as you go. But what you end up with is an output that writes your best learned parameters based on that best loss, and then your final learned parameters as well. So if you train it for a very long time, it may have converged, but you may have kept going with the training. You'll have a track of those last parameters that were learned, but also of the parameters associated with that point that minimized your loss during training. And that's the one that we typically use. If you want to view the raw results, you can just run, whether you're using Windows or not, a command to display that in your command line. In this example, I think we have 48-some thousand. So I'm not going to do that because it's just huge. But we can read it in, right? We take our best parameters JSON file, read it back into Python. And we can see here now we've got our item difficulties. So right, these are sorted. We've got some that are very small. Some go up to very large. Again, it's a function of like the model, the data, and that variational learning process. If you've got certain examples that all of the models answered correctly to the variational inference fitting, that is very easy. So very easy could mean like anywhere from 4 to much smaller than that. So we've got some of those values, and then in terms of ability, right, we've got some that are high ability, some that are medium ability. again, for COLA on glue, most of the questions were answered correctly by most of the models. So we've got this skew of like very easy questions, very high ability models. But we'll see with the squad example, more variety in terms of the response patterns give you better fits as well. But the takeaway then is with just, this command line, you can train your model, you get these outputs, and now you can use these difficulty parameters to analyze your items. And you can use these ability parameters to analyze your subjects or your test takers, whether they're humans, machine learning models, or some mix, right? If you were to use a 2PL model, you would also have discriminability. 3PL model, you would also have a guessing parameter. So that gives you all these parameters that you need to do your analysis, to do your downstream work. Any questions on this notebook? Yeah, go ahead.
So remember, and so we now have a command line.
Yeah.
Statement.
Oh, absolutely, yeah, so in
In the last notebook, you can see it. If I can get to it around Zoom.
I probably glossed over it too fast, but yes.
So yeah, this chunk here is roughly equivalent to what we do in the command line, where you instantiate your configurations, where you define your model type. In this case, it's tutorial, but you could define a 1PL, how frequently you're logging, if you're going to incorporate dropout, and then you instantiate a model trainer, and then you run train on that trainer. Yeah. So this is equivalent to the command line argument that is above the very messy logs. I'm not going to be able to get back to. Yeah. Okay. Good question. Thanks.
One question, the responses are already given, or they can be partially correct. Maybe some task, like summarization is not be completely wrong.
Yeah, as we have it set up now, it's binary, right? Correct or incorrect. Item response theory is flexible enough to incorporate what you sometimes are referred to as graded responses. So you think of something like a Likert scale, right? Like not satisfied up to somewhat satisfied up to very satisfied, or incorrect, partially correct, correct. So again, that would just be another probabilistic model that you define in the package, and you could use that to then train with your response pattern data would look different. You'd have 0.51 or 0.12, whatever it is. But that would be like a graded response model that you could implement.
Yeah, so like you assume in this case that the data is drawn from a Bernoulli distribution.
Right.
But you could choose a different distribution that reflects the rather than it being 1, 0, it being the output, I guess, type that matches the data that you have.
Right. Yeah, so you're making different probabilistic assumptions that you can encode in Pyro under the hood and then plug into train. Yeah. Okay. So that's it for that section. It's time for a break. We'll take 15 minutes. Wow, we're almost right on time. We'll get back together at 10:50. And if you have questions, come up and let us know. Thank you. Morning.
It's like now we're more relevant because like, oh, yeah, it's something. Right. But like, relevant. So much better. previously, we may not have a need for the policy. Other slightly. Super. But they don't. The shift is from a. But more and positive, negative, or. Good sentiment. Yes. Yeah. There's also. Yeah. I guess that's the last. You know, I mean, it's already. Make sure that. Like ours. Oh, exactly. It's way. Exactly. I'm getting very. It's small. That also a little it's a different story. But yeah, that's the thing we're doing. What do we like I said, in fact, school sound perhaps yeah, there again, it's small. We're at spring. When you're at the similar place. So yeah, that's absolutely not already assuming it's gonna the same thing. Basically, answer very and we these groups I mean, that it sounds like this is very relevant here. That's the situation. Yeah, only it's only yeah. Yeah, seems to be for recording your answers, you can say sentences and then correct. But you're gonna ask, what you say that it's a very mild answer. It's nice. In the case like girl, and I used to what do you get to yeah, it's fun. Yeah. is, yeah, there, yeah, so it's not, you should know. But there was a paper about that one. But they were like,
Yes. These will, some of the events with maybe we have to. Yeah. Yeah, yeah, locally. We're seeing, we're seeing that really us in the. Maybe they don't know this, not super. The arm is kind of. At least.
Yeah. 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 That is like basically. But I mean, exactly, yeah, I agree that it's. Yeah, I think that. Yeah, we have to see all of it in one and not.
Hi. Yeah. Nice to meet you. Yeah, okay, so, yeah. So.
Nope, we're good.
Valuation of NLP or. So I think, yeah, that's what I think. That, yeah, depends on the, yeah. Sorry. Well, that one, I'm back to you. I got 82 out of 23 because I found it better than just like 5%. Oh, 32 okay. Oh, that's it. That's it. Midnight snack. And I'm like, I'm getting fingers, I'm generating fingers, just to make sure that I can really drive, like. I'm like, they use this, it's fine.
Because there was one of the things that was annoying about constructability for some runs could be still. And
Yeah.
but I live in the thing figure out the put.
We so I have to write out the camera. Let's see, like, oh. Dimensions here, and then compare it to the slides in the environment. Yeah, but what was here, it was a lot of it. Yeah, and then one thing is the test is with all the things that I got, doesn't seem to be able to spot. Everything else was like, very once it's, yeah, one thing is ready to.
Yeah.
And it was getting better.
The other thing he went. Yeah. The whole first part, getting and put into a box. We have to relearn.
You'd relearn it. The main difference you'd have is, no, because I just changed this for the tutorial to make it easier.
So I have one.
I wouldn't, but this is just as a note for future, but you can change this, just this sampling statement from normal to log normal. And the guide statement as well. I think I actually have the original one. Here, so you change these two. Actually, no, this is the same. Where's the log normal? Here, the log normal, you change it there, and then aside from that, then that kind of resolves the you lose the ability to have negative discriminability if there are some example
Actually, did. But, yeah.
Any sort of things. Experiments,
Yeah.
which is that we can use the.
Yeah, because this is good. But future reference. Fitting model.
I will do that. Let's see. Strange. I think it's like this. I challenged the author about this result. He said, this is a perfect solution.
Assuming that the data already have the description of the location. Negative. But it's just changing. Yeah. Yeah, the mapping is, yeah, example, that truly are. That. The question is answered. That is actually true. That.
Always had.
Yeah. The other thing I think would be spot probably has. Negative discrimination and. Because you. That's all. Good model. Yeah, what is everything? Hopefully the results are. No, no, very good. It's funny.
But that's every.
So yeah, that's true. Yeah. That's true. Yeah.
Yeah.
Very.
Tell them to start.
You gotta bring the try, it's very, very try, like that. You mind if I break some food? So we have to break in 7 minutes.
So we could just start trying together. Start.
Yeah, you see the make up the time. Session. Yeah. I think we'll talk about the shower. I know, yeah, I think we might, Peter was just saying the official break-ins at 11, so we might. Chance to get to that, I realized I had it scheduled in the program. I heard it.
Can you hear this, Joe?
Yep, that's perfect. Thank you.
Perfect. We'll use it.
The copy break can end in 4 minutes, you know. So I'm gonna get 4 minutes, so I'll just give them 4 minutes, 7, trying to yell at them. And our second break will either be much shorter or we'll just say like if you need to go after the. Yeah.
When you said that you can change the,
Yeah.
for instance, for a scale, length of items, yeah. How will you do that? Because these guys, they have incorporated the business units. Why, so it's not that, maybe some of the other.
Right. So you have changes the product itself. Yeah. And it also should. Yeah.
No, but that's, I haven't mentioned that. Because I want to allocate to, meetings, but just a quick one. And they're really involved about it.
Yeah.
And I think they'll have some of the extensions.
Yeah.
And I.
Yeah, they have an R, like, I think they call them grade, or they call them. Yeah, like that. I was thinking about that.
So that's what. Yeah, and of course, probably that's the reason why I haven't seen it that much.
Yeah.
The scale.
Exactly,
Yeah.
yeah.
In the beta one, and I think it's the scale, because I haven't, when it comes to. Okay, this is not really a problem. This is.
Yeah.
It's anyway.
I mean, you would probably see. Yeah.
And in some of the ones you have.
Yeah,
It's like,
yeah.
see that you assume that it was like, I'm seeing.
See that.
So I think it's more like a private center.
Right.
I expect to have center to the age, but then the shade.
Yeah.
I've seen.
Oh, yeah, yeah.
For the stand up. You know, we don't have-
At least, I was a little of the G. They expect us to be. Right, only this. And when they are fast, they are like, by going to distribution and administrative, but they don't, no, you have to change your market. It's only that's.
Yeah, yeah. Yeah, that's something that. Keep going. Yeah, now we're. You start with a couple of initial ones, and then I do I got rid of first one, just the training data dynamics. Then heads back on. Good. Okay. Can you just let everybody know?
All right, let's get the second part of this started. Hope the coffee break was good. So in this next section, we're going to be talking about applications for IRT. Also a reminder, there are some virtual participants and there's a mic there, and I'd really appreciate if we use the mic to ask questions.
So if you have questions, raise your hand. I'll bring the mic to you.
Okay, so in this section, we'll go over improving model training. So John will talk about that. And then I'll talk about one paper in which we used IRT to find annotation error and to look at evaluation metrics. So there are at least 3 use cases for IRT that I can think of in NLP. One is for dataset construction, one is for improving model training, and one is for improving evaluation. So in most of the rest of the slides, and hopefully this is not too repetitive, we're going to assume that the data and parameterization is that we have a data set of items, and those are the test examples, a set of subjects and responses on each particular item, which is binary, but in principle, it could vary, as you asked before. And for this particular model, we're going to assume that there's a discrimination parameter, which is in the previous slides was A, but in these slides is gamma. So to get a little bit of intuition how all these vary, and John talked about some of this before, but to kind of refresh memory on this. If we vary, this plot is showing for a set difficulty, so setting beta to 0, how the theta parameter varies in skill. The main thing I want to point out here is the 2 things. One, the feasibility parameter, which we'll cover in one of the papers. Basically, as this feasibility parameter goes lower, that means a lower fraction of the like the question is not feasible by any model at all. So that's one way that we find annotation error. And the other is by the discriminability of the item. In this case, if the item is highly discriminative, then it is easier to distinguish between models that are nearby in skill. If the discriminability is lower than models that are nearby in skill, it's harder to distinguish between the 2. So we're going to consider 2 situations. What if the data set we want to build is training data? And what if the data set we want to build is test data? So for the first case, John is going to talk about using IRT to improve model training by training models more efficiently.
Okay, so as we mentioned at the end of the last section, once we have these learned parameters, we want to kind of use them, right? So with the improving model training scenario, the motivation with this was we have, let's just say 50,000 items in our training data set. Can we gain some efficiency by using a sample of that data set or a subset of that data set that only includes maybe say the easiest examples up to a point or the hardest examples up to a point, to do something like a hard example mining or facilitate some kind of curriculum learning, right? Where more and more difficult examples are introduced over time. Or maybe we want just those examples that don't include the outliers, right? So if we want things that are a little bit easy, a little bit hard, but not super easy, not super hard, is that data subsetting reasonable and a way to actually get us to efficient model training? Okay, so in a paper from 2019, what we did was we ran this on SNLI and SSTB, and what we proposed were a couple of different strategies. Some of them were using the IRT parameters, but we also used 2% correct benchmarks to compare against just a raw, okay, this question was answered correctly by 90% of the models. This question was answered correctly by 10% of the models. Maybe this is a good one, maybe this is a bad one, right? So some of the strategies that we applied, we called AVI for absolute value inside. So if the absolute value of the difficulty parameter was below some threshold. So that's the case where it's the not too easy, not too hard. We're excluding those outliers on both ends. AVO is the opposite, where we only want those outliers. We want those easiest ones and those hardest ones. See if that's reasonable. We can set an upper bound where we include any data point above or below some threshold of difficulty, or a lower bound, which is more of like a hard example mining case where we don't include those easiest examples. So what we see is, as we vary these categories, we can get close to, full data set performance in terms of the dotted line here for model training with a very small subset of the data set, particularly with the AVI strategy, where we take the kind of, not too easy, not too hard examples, those in the middle, with as little as, 10% of the training data, 25% of the training data, we're very close to the ceiling of performance if we had used the entire data set. And then other strategies are, slightly less effective, but one of the takeaways was the percent correct strategies aren't a kind of stand-in replacement for some of these IRT strategies, because as you can imagine, difficulty and percent correct are often correlated, but you're not containing the same information. So what we wanted to show with this is that there is value in actually learning these IRT parameters beyond just calculating percent correct. And that was evidenced in the data set filtering here. So there's methods for being efficient about what is included in your training set, in contrast to just getting as much data as possible, kind of throwing it all in and letting the model learn. Now these were with, LSTM, the neural semantic encoder models. When we did this, certainly worth, investigating this now in the era of LLMs. But you can think of like particular examples at particular different difficulty levels and their effect on fine tuning and things like that, with similar strategies. What was interesting to us as part of this process was we were also able to do a qualitative analysis of items that humans found very difficult, but the model architectures found very easy, and vice versa. Questions that the humans found very easy, but the model architectures found very difficult. So we have here are the difficulty ranking. Hardest is ranked first, easiest is ranked like with a very high ranking value. For the human response pattern, remember we had originally that data set from MTurk, that's the human column. And then LSTM and NFC are the two model architectures that we used in our artificial crowd construction. So this first example here, what this is saying here is this was very easy for the humans to answer. It's got that difficulty ranking, much lower, but it was very hard for those machine learning models. This was the most difficult one for the LSTM model, and top 5 for the neural semantic encoder model. And what that's saying is that those models had a hard time noting this as contradiction, when in fact the humans saw, okay, 2 dogs playing in the snow, a cat sleeps on the floor, clearly contradiction. Again, some of it's a function of the task. What are you defining as contradiction, right? So you can kind of dig into it and see if this is representative of the category or if this is an outlier in terms of what you expect the category to represent. But, without having this kind of quantified way of, even doing these rankings, you can't start making those qualitative comparisons. This one is actually one of my favorites for the sentiment analysis. I'll give you a second to read it. I've learned not only is this easy for, no, I'm sorry, we have the rankings backward. This is easy for humans and difficult for models. It's also difficult for current students. Everybody in here know who Anthony Hopkins is? Raise your hand if you know who Anthony Hopkins is. He's an actor, yeah, a very good actor. Yeah. So he's, won a bunch of awards, things like that. But if you don't know who Anthony Hopkins is, you have no idea if this is positive or negative, right? Because he could be me, like I'm a terrible actor, right? That changes the review significantly. But for a human, and I guess the humans on MTurk who have seen Silence of the Lambs, they knew right off the bat, all right, the signal of that particular named entity, right, is giving you the the piece of information you need to note this as positive. But if a model doesn't have any kind of knowledge base or any kind of representation associated with Anthony Hopkins, it's going to put this at neutral, or it's going to say, I'm not sure. You get a lot of variety, right? Some will say positive, some will say negative. So again, digging into the details here from like a qualitative analysis, error analysis type standpoint, you can do that now with these parameters to say, what are those ones where there's discrepancies? What are those ones where there's a lot of overlap, right? What's easy for humans and models? Because that's also going to be interesting to look at as well. Okay, so I'm going to pass it back to Pedro. He's going to talk more about sorry, questions, yeah. Yeah, so I had it backwards and I apologize. The smaller number means it's easier. Yeah.
I don't know if you follow up.
Question with a microphone as well.
Oh, yeah.
Okay, with full volume now. My question was the difficulty ranking. The small numbers means more difficult, less difficult?
The small number means easier. Yeah, I
Easier.
had it backwards.
Okay.
The
So
big number
the
means more
Anthony Hopkins question was easy for humans, hard for models.
Exactly.
Okay.
Exactly. Yep. And then this was the inverse. So this cats and dogs was hard for humans, easy for models. And then this one was also, so the negative sentiment is hard for humans because I think it's that neutral. It could be a little positive, could be a little negative, but it was easier for the models. Picked up on certain keywords, something
So
like that.
2 dogs playing in snow, cat sleeps on floor is difficult for humans.
Yes, and
Okay.
I believe it's because they kept marking it as neutral, not contradiction.
Oh.
Yeah.
Actually,
that's-
this is a good question. When like so far in the modeling, we've seen sort of yes, no questions in the like the responses are 0 or 1.
Mhm.
But actually in SNLI, you have contradiction, neutral, and tilde, which do you sort of do these as multiple questions as in 0, 1 for contradiction, 0, 1 for neutral, 0, 1 for entailed, or is this a continuum of as in actually neutral would be closer to entailed than contradiction and entailment?
Yeah, so that's a great question. And it's typically can be done one of two ways. So one, you can say for the overall task of, NLI, then it's correct or incorrect if you get the precise label correct, if you pick one of the other two incorrect. But you could also have subsets where you're specifically looking at, is our ability with respect to contradiction, is our ability with respect to entailment, or you could set one up where is it our ability with respect to distinguishing between contradiction and neutral, right? And then you grade accordingly and you filter out if there's entailment. So it depends on how you set up the response patterns. But these are all with respect to the NLI as a whole task. So did you label it correctly or not? But yeah, I mean, there's a difference between like contradiction neutral and like entailment contradiction, entailment neutral. So
Yeah.
it gets interesting to dig into the differences for sure.
Yeah, thank you.
All right, thanks. Say it again.
First example,
Oh,
For the first example, true label is neutral or contradiction.
no, the true label is contradiction, but the human annotators kept picking neutral.
Okay,
So it was hard. They got it wrong more frequently.
okay, okay.
Yeah.
Yeah, understood. For me also, I think it's neutral.
Well, exactly, right,
Yeah.
yeah, and that's a function of, maybe this is an annotation
Okay,
issue or
Yeah.
a task description issue, yeah, it's gotta be a bit more precise, yeah. Right, all right, thanks, so now I will pass it back to Pedro.
Okay, so next I'll talk about how you can use RT to find annotation error. So overall, test examples can fall into multiple different categories. They can be too hard, they can be too easy, or they can be just right. So in this case, the yellow and the orange are more of the just right kind of questions. And distributed across all these categories is annotation error. So when you're comparing, say, two data sets, so the top here represents one data set, the bottom represents another data set. These proportions are in general going to be different. And in both cases, what you would like to do is be able to identify which questions are too easy, too hard, but also where the annotation error is. So in this section, I'll go through an example of how to find annotation error, and then I'll talk about the paper which we did that for Squad. So what are some things that make examples bad? So examples that don't discriminate between good and bad subjects fall into this category, or where the label is bad and all models get it wrong, or correctness is a coin flip, or it's just random and it's not related to the models. A general non-example is just a difficult example, because if a model happens to get it correct, that gives you a lot of information that it's a good model. So a difficult example is not inherently bad. And the way that we're going to find this is using the discriminability parameter gamma to define these. So there is a notebook that you can follow along. All the results have been copied into the slides. But if you want to see everything run, that's in the notebook on the website. So in this notebook, we ran a simulation where we have, again, 10 subjects where the ability and skills uniform -4 to 4. We have 1,000 items where the difficulty is also in that same range. We will assume that 5% of the items are invalid, and that if the item is valid, then we follow the IRT equation to decide if the response is correct. Otherwise, we flip the coin. And then we train a 3PL IRT model with pi IRT. For these, we sample according to these. So we assume that the difficulty is normally distributed. The discriminability is log normal. So the discriminability is strictly positive, and that the subjectability is normal. We discussed this a little bit. There's different choices for your priors for all of these that you can have, and they have different effects. In this case, we picked log normal because that makes it very simple to understand discriminability, that if it's positive, that means it's a more useful example. If it's negative, it's not a very useful example. So in PyIRT, this is the simple way to call the model that we're doing here. This model is called the tutorial model, but it's really just a model that has discriminability, ability, and difficulty. So this answers someone's question. Can you run the code in your own code? This is how you do it. So can we distinguish the invalid items based on discriminability is the main thing that we want to see that we can find here. So if we plot all the invalid items on the top and all the valid items on the bottom, then yes, we see that all the invalid items that we know are invalid because that's part of the data generative process are on the left side for negative discriminability versus all the good examples are in the positive end. So where we did this in a paper was doing this same process for SWOD. Our model was slightly different. So I'll talk about the differences in this model. We introduced a feasibility parameter here to represent whether a given example was answerable at all. And we did this so it'd be easy to look at examples that have low feasibility or low discrimination. The other thing that we did was we allowed discriminability to be negative in this work because we knew there were examples in SQUAD that had the wrong answer and all models would do worse. So we plotted all the examples here, and what we looked at were different categories of examples. And for each of these categories, we annotated a set of examples on them. So we took all the easy examples, all the hardest examples, all the examples that had low discrimination and high discriminative power. And we annotated those to see, well, do we see what we expect? Is there annotation error or not? So in the plots I'm going to show, I'm basically asking for a given example, was that example correct in the sense it's a valid, good question, and that the answer is correct and there's no ambiguity in like anywhere in the question. If that is true, then it'll appear in this big blue bar. If there's something at issue with the question, then it'll appear in either the flawed or the wrong column. And I'll have an example after the next slide. So the factors that we compared were, well, what if we look at all the high difficulty questions? All those questions seemed fine to us. All the low difficulty questions, mostly were fine. Where we ran into lots of questions that we thought were just bad questions was in the negative discriminability category. So it could be anywhere from, like this red represents it was an incomplete answer, to this green, the answer is only partially correct, or this purple that the answer was ambiguous or the answer is just missing from the answer text. So an example of the kind of questions that we were able to easily find is this example in SQUAD that asks, why did the demand for rentals decrease? And the official answer in the data set is demand for higher quality housing. But if you look at the text, the number of high quality rentals decreases, demand for high quality housing increased. So the question just doesn't make sense because the demand for high quality housing increased, not decreased. So it's a bad assumption of the question. So these are the kinds of examples that we were able to much more easily find. And then the next step is remove those examples from the data set so that your data set is better. Any questions on this?
Thanks.
Should this always be that the feasibility should also be low in these cases? Because even if you, for example, answer randomly, you should only reach a certain percentage of answering it correctly?
Yeah, so in this case, it varies on the task. So in SQUAD, it's a task where in Squad, you highlight your answer in the context. Versus something like SNOI where you have a certain number of labels, so say 3 labels. So if you guess at random in SNOI, you have some random probability that you'll just get it correct. The random guessing likelihood in Squad, I'm guessing, is pretty low if you just randomly select a passage. In some sense, we over parameterized this for looking for bad examples because the feasibility could be low for bad examples, or the discriminability could be low, and either one would be reflective of a bad example.
No, we talked about this a bit during the break, but I mean, in this kind of setting where you're trying to find annotation error, then like, do you need what 3 annotation per sample, or like more, or like how many items do you need to have a reliable model for this purpose?
So one, I guess one answer could be if what you want to do is rank models well, then yes, you want a certain amount of examples. But the use case for finding annotation error here is an aid to whoever's building the data set. So as long as the data set could be small, but as long as you're finding value in using that tool to help you find bad examples, I think that's still helpful in terms of like in practice, the number of examples that are useful to have. I haven't tested personally like lower scale because all the machine learning data sets are like, we have at least 1,000 examples, because if you submit a paper that has like an evaluation set that's any less than like 1,000, then they might not get in. But I think with 1,000 examples and you know, not that many models, it still ends up being useful.
Yeah, and some of the work that I've done, I've also seen that even with like 100 annotations, if we're looking at particular items, we can already we're already able to start to see errors in particular items, because we'll see that the gamma is like either very uncertain to calculate, or closer to basically being at like closer to 0, so it's not even, you really can't tell.
Good for. Other questions before moving on to evaluation metrics?
Yeah, sure.
Could you go back to the squat example? So how should we interpolate the feasibility being 0.6 for this example?
The feasibility?
Yeah.
Yeah, so in this particular model, I think we allowed for 2 ways for bad examples to be detected, so to speak. So to me, it's not that surprising that the feasibility doesn't necessarily agree with the discriminability, because if I go back to this, if the discriminability is negative low, then that messes with this equation already. Like, you don't need both factors to be making this problematic. So only one is needed. That's kind of one, you might argue that's one way to say, well, maybe we don't need the feasibility parameter if we have just the discrimination parameter. But for tasks like SNOI, where there's actually a reasonable chance of guessing correctly, you want to incorporate that. So you would incorporate, there's a factor here that's like your random rate. So for SNOI, it would be like 1/3 plus 1/3 minus this, and that would basically say how much is the IRT part, or how much is this correctness varying like above or below the random chance. So if I were doing this again, I'm not totally sure I'd need feasibility. That's maybe one way to put it, but it would be interesting to check that. Okay, so the other thing that we've looked at is evaluation metrics. So one way that you could see this is, well, just instead of accuracy, let's just rank by ability. And that's somewhat helpful. But I think if you're using it as a total ranking, it doesn't really get at what IRT is very useful for and very effective for. Because if you have 10,000 test questions, then you can get a reasonably well calibrated sense of like how a model is doing. So in this paper, we looked at something which I think is actually very relevant now. And instead, what we are interested in is, as before, we have the same number of test examples, but we changed the setup very slightly. And we have, sorry, that's the next example that I'm talking about. In this example, what we want to do is be able to distinguish between easy, moderate, and hard examples. And in this experiment, I'm basically varying the validity rate of these examples. And the supposition I have about the data, if I do something like this, is that hard examples are harder to create. So I have both fewer of them, but I also have a lower rate of getting them correct. That assumption could be right or wrong, but that's the assumption of this particular simulation. So in the table that I'm going to show, I ran this simulation with this slightly modified data sequence from the example before. And the table is going to show the true ability, the IRT inferred ability, and then the accuracy on each different subset. So the overall accuracy, the easy accuracy, the moderate accuracy, and the hard accuracy. And what does the data show? So the main highlights I want to make here is the variation in true and inferred ability and accuracy by subset. So if the true ability is pretty low, then the main dominator of the main thing that's changing is the easy accuracy, which makes sense. If the true ability is around the center, then the main thing that's changing the accuracy is the main area of change for accuracy is the moderate examples. And at the top end, the hard examples are where things are changing as well. Yes. So the simulation is set up so that we suppose that all of this is true. So we're going to take a subject and sample their ability randomly, uniform -4 to 4. Whatever that value actually did turn out to be sampled is what I'm calling the true.
Okay.
Because in general, the generative process, if we have like models, we will never know what their true ability is, because that's a latent variable that we're trying to infer what a likely value is for that. So the reason I'm setting up these simulations is to have like intuition and say, yes, if we make these assumptions, we see that IRT finds those same assumptions. And then at least, yeah, and in these same set of slides also, like, then we did the same thing in a paper and it seems to work. The other thing I want to highlight, because this is one area where IRT is quite good, is we have fewer hard examples because there are only 50 hard examples, and I also intentionally made them more noisy. So the accuracy differences here, for example, around 0, these vary quite a bit, 4%, 4%, 10%. And that's something that is more and more relevant as we get to the top of leaderboards, because as we get to the top of leaderboards, the only questions that remain are the hard questions, and there's not that many hard questions. And that's also where annotation error tends to creep in. So that's one of the reasons that we think IRT is useful in that particular domain, because we can explicitly model the noise, and having a discrimination parameter or feasibility parameter that gives us room to incorporate this extra piece of information. And that the accuracy differences here are not that big, which is not dissimilar from how leaderboards are set up either. So showing the same plot as before, we can see that invalid examples are also still sorted down. We also see that as we set up in the simulation, that the hard examples have a higher rate of bad examples being generated, and that's also represented here. So IRT does a good job of basically detecting, oh, this is the bad example, ejected out. But still that you have hard examples here that are valid, that are informative, because if a model gets a hard example right, that gives you a lot of information about how good that model is. So the reason that this matters is that noisy examples give us noisy metrics, which ultimately gives us noisy rankings of models. And if you want to claim soda, you need to, have not a noisy ranking. So IRT is one way to mitigate the effect of noisy examples by directly modeling that. And the other useful thing is we don't need as many examples. So I'll talk about in this paper how we assume that, how we set up a situation where we could find out how few examples we can annotate in order to get a reliable ranking. So we're going to assume that the cost of annotation of model responses is high. In this paper, we are working with squad. So actually getting the correctness of a given answer is not high, but I think now in the realm of grading generative AI models, it's more relevant. We have pre-existing leaderboard data. In this case, squads, we have the response matrix. And we have a new set of subjects or models that we want to evaluate. When we want to minimize the annotation cost and maximize the correlation to the ranking that we generate with if we had used all the data instead. So the way that we set this up is we took the squad leaderboard and all the models, we split 80% of the models and 20% of the models into a different group. Then for different ranges of experiment sizes and different ways of sampling questions, we iteratively chose M items according to the sampling method. So for example, let's say that we picked questions by the most difficult IRT parameter. So we would pick either 16 or 32 or 64 up to 10,000. And then rank models according to that, or rank models according to the discrimination parameter. And then compute the correlation of the rankings generated from this sample with this particular method to what the rankings would be if you use all the test questions. And the reason why this is 10,000 is because the dev set for squad is actually 20,000. But we wanted to essentially have our own like mini dev set that's completely separate. So we use the other half of the dev set to compare rankings, because you would hope that the ranking on one half of the dev set would correlate to the other half if you randomly sample. What we basically saw was if we pick at random, the random method of sampling is not that great. If we are interested in how many examples we pick and the correlation of the resulting ranking to the test rank. If we do something very simple, like just say, well, I'm just going to pick the examples that have the highest discrimination value, we do far better with something closer to like 0.8 Kendall-Tau correlation. There is an even better strategy that was kind of implied by one of the earlier slides, which is I can pick examples that are the most informative. And most informative is defined by this equation. Reading this is basically just gamma squared. So a high discriminability value is good. And this encodes a different intuition where if we had two models and we wanted to extract the most information, what we want to do is ask a question in which one model that we're in that discrimination area of where we had the item characteristic curve earlier, that it's easy to distinguish between one or the other. And that happens when this probability of the model getting a particular question correct is 0.5, because that's the most entropic event that you have if you have just normal probability from 1 to 0. And as we would expect, that method overall does better, even if at the beginning it doesn't. The other thing to note is that the number of examples you have to pick is relatively small. You only need, say, 300 or 500 examples for this method to work well. I will pause real quick if there's questions on this, because then I'll highlight some work that has similar goals before we move on to the section after this. Cool. So we're not the only ones that are interested in this kind of thing where we do essentially our goal is to have efficient evaluation of models by not using so many examples. One I would probably highlight that's here is the anchor points paper because it's here at EACL or was earlier. But all these papers are papers that in one way or another are trying to look at this question of how can we do efficient evaluation by using fewer examples, some of these with IRT and some non-IRT methods. And we're not going to do the back in 15 minutes because we had the coffee break already, right?
Yeah, so in the interest of time, we're just going to keep going. But if you need to step out, use the restroom or grab coffee or water, please feel free. So next up is Jose.
Okay, so what we've seen so far is basically that IRT is relatively straightforward, especially if you use some of the libraries that make it easy for you. You just take a set of models and you don't need to know anything else. Basically, you extract all of these insights just by running this. Of course, you have to be careful and try to interpret the parameters and all of that. But you don't have to make many assumptions about what you're measuring. And it's basically, okay, you take a task and you just extract all of these parameters. And sometimes you need to play with 1PL, 2PL, or maybe some of these things. But it is out of the box and it gives you a lot of advantages. But of course, in a way, it has some limitations, and there has been a lot of work in terms of extending IRT or alternatives to IRT or some kind of and most of them are based on the idea of looking at the instances, which is item response theory. It is based on looking at items, not looking at aggregate scores. I think that's the main difference. So what I'm going to talk about is advanced topics in ways that IRT can be extended for some of the limitations or areas where maybe we think that we could use something different, and of course, some kind of extensions. So what are the main limitations of classical IRT? Because IRT is much more than what we have seen. So some of the models I'm going to talk about are also part of IRT. So one of the things that you may wonder here is, okay, why just logistic? Do we have some other models? I think the interesting thing here, or it's we have this kind of thing between the ability and the difficulty. This is a subtraction. We calculate something that I usually call the margin. And with that margin, it's going to be this positive, this is going to go well. If it is negative, this is going to go bad. And then you have a logistic function, which naturally maps that into a probability. So that's fantastic, but there are many other ways in which you can do that, especially when the output is not Bernoulli. Then the other thing that has also come up in the discussion is that we only map one dimension. And that's good when you don't want to get more insight than just, okay, difficult, easy instances, but especially in the days of general purpose systems, and I don't come from NLP, I come from some other areas in machine learning or AI. So what we find these days is that we have these systems that are able to solve a wide range of tasks. So maybe one single dimension is not enough. But then, of course, the complexity increases in terms of how many dimensions, how are these dimensions interacting. So this is one kind of limitation. There's only one dimension, only one ability, and of course, opposing to that ability, the difficulty. And of course, all the other parameters go around that. But even if we go to many dimensions, are these dimensions related in some way? And if you go to especially psychometrics or psychology, they start with all of these hierarchies of capabilities, of skills, and some skills are more general, some other skills are more specific. Can we do something similar here? And a fourth limitation is, imagine you have a new instance, you haven't tried that instance with any of the models. And you have a model that has capability or ability 3.2. What can you say? Nothing. With this, you have to take this instance, put it into the pool, and take the difficulty parameters and all the parameters. And once you have that, you can predict for that instance. But that forces you just to put that instance into the pool. Can we just, for an instance out of the blue, just predict something? Can we say for a model that we have already evaluated how well this model is going to perform for a new instance? So that's kind of predictability is something that we don't have out of the box in IRT, but there's some kind of models in IRT that try to extend for this. And the best thing about IRT is it is populational, but also sometimes it has a limitation because you have to choose that population and it is depending on that population. If you change the pool of models, then you're going to get different parameters. And then you say, oh, then what we're estimating is not actually the ability. Well, it's subjective to or relative to that population. And we have to be very careful about that. So they are not absolute abilities, but relative abilities to that population. So we are going to talk a little bit about some extensions and variants that try to cover some of these things. So I think in IRT itself, you find many solutions for the first three problems. There are some kind of extensions, multidimensional IRT. And for 4, you have what is called LLTM, which is kind of a linear models of difficulty. We will see that in a moment. And issue 5, this is probably the thing that people who are new to IRT or even people say, oh, but this is, well, I think this is one of the features of IRT, but still, if you don't like it, there's some alternatives. And these alternatives are closely related to IRT. So everything that you have learned today about IRT, you have been playing with IRT, all of this is going to extrapolate very well to these alternatives. So in terms of non-logistic IRT models, so sometimes you don't have, in the old days, actually, why did psychometricians choose the IRT models as logistic? Because for instance, the ogive model was much more complicated to estimate. Just that was a simple reason, not because logistic. The old models in 60s or 70s, just imagine compared to modern machine learning. So what they could do, what they could infer, which is dozens of examples and dozens of models. But today you can do even some kind of some other sigmoid functions. And even you could try with a kind of a step function. You could do that, of course. I don't recommend it, but that's the old Goodman model. But more interestingly than that, because I think that the logistic model is quite good for what we want, is when you're thinking about the Bernoulli distribution, that's what comes to mind. But what if you have a score that goes between 0 and 1? And that happens very often in many, just a score for each instance, or even you have a score that is not between 0 and 1, but you can normalize it into just a finite interval. Then a normal distribution as an output is not the good solution. The Bernoulli is not a good solution. So there have been a couple of new models just using the beta model. And this beta model is parameterized in a different way, and the parameters, they have different names. Some of them can be mapped to discriminability, to difficulty. So just take a look at these papers if you are interested. And there are also some kind of, I think there's also some code as well, just to run them. But yeah, another option is maybe you can read this and adapt them to IRT. And in regression, you can discretize that. But in situations where you have a loss that, for instance, goes between 0 and infinity, you can use a gamma distribution. So this is another approach, another model. All of these references, if you're interested, they are in the reference list. Of course, we don't have time to go through all of them, but just to see that all of these models there are more models, and you can get even aspiration if the distribution of your output is different, just to maybe introduce your own model. So the multidimensional models, I think that's the most interesting thing in terms of the extension of IRT, which is what if we think that several abilities are required for solving the items that we have in this, or maybe we have a wide range of tasks being combined. This happens a lot these days with large language models when we want to evaluate them. Just one single capability, we think that maybe that's not going to be enough. So basically, there are many formulations of this. One basic formulation for sorry that you see the the exponential twice, but it's the same model. But just I'm just using the notation that some of these books use. I don't like it, but yeah, just to follow the notation there. But basically, what they do is just they convert the ability into a vector, and then what you estimate is you estimate also the weights of that vector as well. So there are many more parameters here. So how to estimate them? You can find some of the answers there. There are many other models, and you can follow multi-dimensionality. There are many more things, especially for this recent book about that. And one of the questions, imagine you are just building in NLP, you're just building something translating from natural language to SQL queries, something like that. I think, okay, I think that one single ability is not going to be enough. So what about dealing with negation? That could be an ability, and another one, dealing with quantifiers. And can I model different approaches for that and say, okay, maybe I have an ability 7 for dealing with negation, but that model has ability 0 for dealing with a universal quantification or existential quantification. If you had students about SQL, you feel that. Humans, sometimes they are very good at negation and you're surprised that they're very bad at quantification. And that might happen with some, you can try some large language models for this task and see, okay, what happens where in, and you have these two capabilities and use some of these models. The question here is, does some kind of high capability in maybe dealing with negation helps in limitations that you have in universal quantification or quantification in general? So for that, the literature has introduced two different approaches. One is called the compensatory, where high levels of one ability can compensate for low levels of the other ability. So here you have an example on the right. Here you can see that you have a lot of these theta 1, you can get to 1, even if you have a very low theta 2. So a high capability of theta 1 can compensate for no capability at all in theta 2. But in this case, this is asymmetric. Theta 2 can compensate for, in many cases, for high capability of theta, because this kind of a shape that you have. So what are the equations here? Yeah, you go to some of these sources, you will see the equations. Sometimes they are kind of complicated. And there are many variants in the way you can combine these two capabilities. This is a non-compensatory version. The formulas are different. Sometimes, to add to the confusion, they are called partially compensatory, but I would call them non-compensatory, because basically, even if you have a high capability 1, this is not going to compensate. So if the item requires both capabilities, you will never do if you only have 1. Okay? So these are the models, and yet there are different formulations. I like a formulation where you take both abilities and you use a generalized mean, and you try to infer what kind of compensatoriness you find in the data about the two abilities, rather than just putting that as a prior or as a kind of a domain knowledge. But yeah, there are many formulations here. So there's a whole field that even books about multidimensionality and some of the things that we expect is some of the extensions of the libraries in this direction. So we are inferring difficulty. This is great, because many times we don't have a clue about what are the things that affect difficulty. But on some other occasions, we know that this might be related to difficulty. Can we use that information for helping the system, or to have a kind of a mapping to some features about the instances that we can identify? So sometimes difficulties or some proxies for difficulties are observable. So here's an example, language models. Just you try to perform addition with them, and then you say, okay, well, some of them are easy, some of them are hard. Still, GPT for failing with 20, 30 digits, quite common. It's quite common you find that, but they don't fail with maybe 5, 10 digits. And the things that you expect to affect difficulty is the number of digits of both summons, the carrying, whether there's carrying or not, and the digit diversity. That's some kind of a guess that okay, I think that these things might depend, may affect and the difficulty. So in this case, I use these 3 features or characteristics as a proxy for difficulty. Okay, but then the question is, do they really contribute to difficulty, and how much each of them? I have the feeling that digits is the most important one, the number of digits, but maybe I'm wrong, especially with language models, because you never know how they're going to behave with these things. And then you can use something there that was introduced some time ago, which they are called linear logistic test models. And if you see here, and sorry again, we see the X twice, but it's the same extension to the traditional logistic models, where we see that we have these queues. So these 3 queues, the values that we have, number of digits, that can be a number, carrying can be just a scale, 0, 1, 2, or the number of times that you have to carry, and the digit diversity can be something like the standard deviation of the digits, or the number of digits, or something like that. So these are the queues, and what you need to learn is this thing here, and then you only have one capability, one ability per model, and basically you think that difficulty is a linear combination of these things, and you need to learn the parameters, the coefficients. Okay, so that's what this LLTM thing does. This is, as you can expect, is relatively simple in terms of, because this is a linear model of that. So you have something like this, and you have values for this for several items, and you have the results. You can put all of this together, and this is kind of an IRT when you start with these 4 proxies of difficulty, and the system is going to learn the coefficients, okay? So you help the system in terms of the difficulty, and then you have this mapping, and you have, okay, then you can learn these coefficients per item. Okay, so this is quite interesting, because now if you have these parameters, if you have a new instance, look that these coefficients, they are not parameterized by instance. So that means you have a new instance, 13 here, and you have new values here. You can predict the performance of that system on that new instance, just if you have this. So I have a new addition I have never seen, I have never tried with my IRT models. I can predict how well the model is going to perform on that. So that's something that we can get from this kind of extension of IRT. But of course, you need to have these proxies. And on many occasions, we don't have them. That's why we use IRT. But on other occasions, you have them. So you can use them, or you can at least try with them. And there's a rule. If you don't get better results with this and the Rush model, don't use it. Because maybe your intuition about these Q proxies, it wasn't good. Sometimes you realize that difficulty, you have an intuition, but it depends on the distribution. And this happens a lot in classification, as you know. So it's that the difficulty is not intrinsic to the instance. So it's much more difficult to determine the difficulty. You can use IRT there, but then you can try to analyze why the population of examples also affects the difficulty of one single example. And when we have difficulties that we can analyze, as in the previous example, as an addition, sometimes the first thing that I do, and I recommend you, is just to, if you have an intuition that something is affecting performance, just plot it. And what you can do is, okay, that thing, in this case, is the number of digits. For 3 models, I think it's GPT-3, 3.5, or 4, I don't remember the versions exactly. What you see is that depending on the number of digits, you have these nice sigmoid curves. about how they behave. So basically that suggests that maybe some kind of a logistic model, some kind of a sigmoid model is going to work well. This is the opposite to the item characteristic curve. This is what people call in the old days, a person response curve, which is basically the other way around, where we have on the x-axis is the difficulty of the instance, and on the half is just the performance depending on that difficulty. And to me, that's very insightful. You have a system that, even if it just shows an intrinsic difficulty or a difficulty that comes from IRT, if it doesn't go that well, then you see that your model is not behaving in conformance to that difficulty. And that means something. That means a lot generally. So you can have something like flat, the model is very bad, but when the models they start to get better, you want these curves to go to the right. And that's much more insightful than just looking at the average performance on the data set, because you don't know how it's basically the same way of looking at this. And you can use original difficulties, observables, proxies, or you can do IRT and do this. So what if you don't have any proxies for the difficulties, but you would like to do some kind of a predictability for new examples? So what you can do is annotating instances in a way that can be automated. So things that you can do, for instance, something similar to topic modeling, but for evaluation would be, okay, can we just use some kind of an annotation, or kind of use some kind of indicators of each instance? Or maybe you can use some kind of syntax or semantic complexity metrics by default. So that's one example that this is what we did. So basically, we tried to compare some kind of a classical syntactic and semantic complexity metrics. And then what we did is, okay, we went through a range of dimensions that we thought that could affect difficulty, such as the uncertainty in the text, the negation, time, space, vocabulary, modality, theory of mind, reasoning. So we were quite wild about this. We are not in NLP, so we were quite brave doing this. And we wrote some kind of a rubric for GPT-4, and we annotated thousands of examples. So in the end, what we did is just getting something like this, but just using GPT-4 as annotator, something that you can do. It's relatively easy, and it's quite reliable in a way. At least when we're having discussions about whether this is better than humans, it's a kind of a. So so with this, this is the task that we used, and we took them from Helm, and the models are on the right. So it's kind of a wide range of models here. And what we did is, instead of using an LLTM model, we did something simpler in this case, which is just we train an XGBoost model on that. And what we got is that using the traditional metrics, sometimes we got this is R squared, but you can see some other metrics in the paper. Sometimes for some of the tasks, we got predictability. For some other tasks, we didn't. So the way all of these, the syntactic or semantic features, they were not predictable, but in some other cases they were. And in the case that they were, we found that these meta features that we annotated, they were in principle better for predicting this. And this is on the right, the difficulty with respect to the predicted difficulty. So in a way, you can, with this XGBoost model, you can predict the actual difficulty quite well. So the interesting thing about this is now you have a new instance. You just go through all of these rubrics, you ask GPT-4, you annotate the example, and then you can predict performance. And how well you can predict performance depends on these numbers. So for some data sets, nothing. For some other data sets, yeah, you can predict performance quite well. So yeah, it's not a surprise that some of the MMLU are the best ones here, and some of the more specific data. But maybe you know better than me. You can get better explanation why this is the case than me, because you know that that's some of these ventures better than me. Yeah, but this was fun. Something that you can also try with this idea of, can I model difficulty for some kind of meta features of the instances? And then you can do much more than that. You can build difficulty models using the original features. You can use some kind of embedding on the questions and try to model difficulty directly. You have some kind of signal. You can use IRT signal as a ground truth, IRT difficulty as a ground truth. You can do many things. That's something that we did here, and whether we were able to predict difficulty, and the results were quite good in terms of being able to have. So with this is you have both the best of both worlds. You can use IRT first. Once you have the difficulties, you build a model of difficulty and you can apply that to new instances. So that gives you IRT in the first place and then predictability in the second place. I'm going to skip this. I don't know, but can we just say build a model that maps from the results? This is a set of instances with all the features. It can be images, it can be text, it can be whatever you like, it can be multimodal. You do that and you have the output. Can I just build a model of that? That's what we call an assessor, which is basically a model that predicts performance at the instance level. And you can use any machine learning tool to do that. Was in NLP, you would use something, and in some other areas you would something, especially because you are taking the whole original feature space as input. So that's basically what you would do. You would get a lot of information from models and instances, and you would try to predict performance. I'm going to skip this. Yeah, we were playing with language models as well, how well you can predict. And it is usually a little bit better than uncertainty estimation. And that's a good thing, because these days, with many private or non-open language models, we don't have the log pros anymore, and it's very difficult to know. And they are not very well calibrated because of the human feedback and all. So having something that tells you how well a model is going to perform for a new instance is something that gives you a lot of value, especially because they're expensive, because maybe in some applications you don't want to run them if you're not sure that they're going to well. You can predict not only success, but you can predict maybe toxicity or something like that. Any metric of output. So here we are talking about correct, incorrect, but everything here, we have been talking about fairness, but we can apply all of this with any signal or any output value. So a more general extension of this is what we call the measurement layers. We had a tutorial about this just a few weeks ago at AAAI. And this is something that we have been working on for a few years, and now we have kind of a library or something. And this is very much IRT inspired. So in the end, it's kind of just a wild generalization. Do whatever you like, but the core thing is still IRT. So if you only have 10 models, maybe this is too little for IRT. And this is the data you have. Maybe you can say, I can create more models, but maybe this is expensive, and that's what you get on Helm or some other library where you have the evaluation of the results of a data set, of a paper, you have only a few models. So what can you do? Again, you try to establish the demands, and here you have many possible ways that could map to difficulty. You try to make a selection, as we discussed before, and they say, okay, I'm going just to stay with the ratio of digits that I have to do a carry operation, the mean of the number of digits of the two summonds, and the standard deviation, which is kind of a diversity. And remember this, you have 1, 1, 1, 1 plus 8, 8, 8, 8, 8, 8. That's a very easy addition because you don't have a lot of, it's kind of a proxies for difficulty. And here we just say, okay, for each of these difficulties or demands, we are going to include one ability. One is called the carry ability, another one is the size ability, another one is the digit variety ability. We assume that they have some distributions, beta distribution. This is kind of we are using PyMC, which is just another probabilistic programming, or this is Markov chain Monte Carlo's library. Maybe you have heard of PyMC. You can put all of this there, and the square boxes in the middle, they're basically IRT. You just subtract the ability and the so each of these things is abstraction, and then you apply a logistic function, and then you try to combine that in a way that is maybe is compensatory or not compensatory. Are these three abilities compensatory or not? And then you can play with that, or you can introduce some kind of weights. Yeah. And then you do this. This is a plate. We have 2,000 and something examples. And then we have what we call a capability profile of the system. But this is not the performance on different tasks. This is just one task. This is just 2,000 examples of addition. This is just one model. We are not looking at what other models are doing. So this is just, for instance, the first thing is just obtained from the data from ADA only. It is not affected by what you get from the other models. So this is not going to change if you add new models to this, because this is done independently. So this is not populational, at least not populational, the model size. And then you get all of that. Sometimes you get more insight. Sometimes you get less insight in terms of where they cross. And of course, you can expect that some of the recent models, they do quite well, and they have, but not always they have the highest value for the three abilities. In this case, the three abilities are quite related, so they're not very independent. So we don't see much, just a proof of concept with something that is quite graspable, such as addition. But you can think, okay, can I, maybe some of these abilities, they are related, and then maybe there's some kind of something that is a sample size that affects the ability, the size ability and the carry ability. Then maybe we can think about some kind of addition ability. If you have some kind of domain knowledge about this, or addition, or any intuition, you can play with all of this. And of course, this takes time, but sometimes you get a model that maybe tells you something, some story about the data. So this is the same, but here with instead of having 3 capabilities, you have 4 capabilities, and you relate that in a different way. So the question is, okay, you do all of these tricky things, you find all of these nice plots, fantastic, but are they really, yeah, how do you evaluate evaluation? Or how do you evaluate that these are really telling you something, or they are good for predicting performance for new instances? So you can do this by just evaluating for fresh examples how good they are. And for instance, you have these 2 things at the bottom, and you can compare that with some other approaches trying to predict. The most powerful one is that you just build a black box classifier here, predictor, and you get something like this kind of typically the tallest one. But sometimes you get quite good results with the measurement layouts. Maybe for some of the recent models, the results are not that good, but still quite good in terms of AUC. And you have some kind of interpretability in terms of what these things mean. And for some domains, you can have more background knowledge about the capabilities that should affect your performance. Okay, so this is more or less some things that you can use as an extension. There are many other things related to IRT in some way. We've been talking about ELO ranking and true skill, and there's a lot of discussion these days about scaling laws. If you're interested, I have a poster relating a little bit of this with the workshop tomorrow about scaling large language models, but that is just, and in psychometrics, you have many other things. So the typical thing when you think about psychometrics and the social sciences, the structural equation modeling, is this the same or not? And of course, factor analysis. And I'm not very pro factor analysis, but you can also try that. You have a population of, because that's not such a thing as a population of, for instance, language models or something like that. But because I'm not very much into factor analysis, I did it myself before some other people could do it. Yeah, so this is a paper we published last year where we did factor analysis to a bunch of language models and tasks. And we identified 3 factors. I wanted to identify one and saying something that there's a kind of a G factor for language models, but yeah, the data disproved me, and yeah, so this is what we get. But yeah, and we can spend hours saying, why is this different than that? What the structural equation model is different from what I present about measurement layouts? Why is this multidimensional? So in a way, all of these are extensions, and the more flexibility that you get these days with especially inference tools, for instance, we're using PyMC, but you can use some other, we have much more powerful than when the models were introduced in the 70s, 80s. So all of this is open for us just to explore. Don't be scared by this table. This is kind of a summary of different approaches. I think the lesson here, before you go into, we get into all the details here, look at the first row. So the first row is what most people, 99% of the people, are doing in evaluation. They basically performance aggregation with some metric, and then it's not predictive for items, it's not predictive for systems. Of course, it doesn't require domain knowledge. Okay, that's okay. It's not population in terms of systems. You don't get abilities, you get performance, but don't mix performance with abilities. Yeah, and then you can, the type of models is basically an aggregate. Basically, you're using a statistical metric, that dispersion at most. So can we do better than that? Yeah. For instance, we have introduced IRT models, and all of these are IRT models here. So they are predictive for items. So if you have seen this item before, and this model has, you have the ability, you can predict how well the model is going to perform for that item. So you have this kind of, these models are predictive for that, for the cases, because you only use the identifiers, you cannot go much beyond that. If you have a new item, you cannot do that. So that's why for some of the things, so for the LLMTM they have just introduced or mentioned, then you can extrapolate for new instances. This is already very good, but this is better. And many of these approaches are just extensions. This is basically a simple extension of IRT. And here you can do this. You can also predict for systems. That's something that you can do with IRT, but these systems must be in the pool. You don't have the ability, then you cannot predict for this system. But can you predict for new systems? And that's something that's happening for scaling laws. What if I have 10 times more parameters? If you parameterize the model as well, you can predict that. So you can have some features about the model. You can use them when you have a new model, then you can use them as parameters for your model, as predictive inputs for your model. And that's something that you can do, and that's useful. Even before trying the model, you can anticipate how well this is going to work. For new tasks, out of the distribution, all of this is open for us to explore. We can do much better than what we are doing. And of course, the big question is, do I need time? Of course, this is very easy. The first row is very easy. Just take the data, calculate and aggregate, and just publish your paper. Okay, fine. And some others, IRT, you don't need a lot of domain knowledge. So that, at least do that. If you don't have any domain knowledge, at least do IRT, or but if you have some domain knowledge about the task, or you have some intuition about what capabilities you want to use to represent especially models or systems, then that's something they can use. I've highlighted in green because it's better that you don't need domain knowledge, because domain knowledge requires time and expertise and all. So that's always a drawback. And one of the discussion has been, is this approach populational? That means that all of our parameters, do they change when we change the pool of models? So when you have a yes here, that's going to change. I think that IRT is quite robust if you change a few models. Of course, if you change all the models, that's going to change a little bit, but it's quite robust. At least what I have played in my experience is we have had some discussion about what kind of, but provided you put some minimal variety in your models, you're going to get some kind of meaningful results. But yeah, they are going to depend on that choice. And the most interesting thing is that you don't get just a number of performance that is tied to the particular distribution that you have in your test set, these are abilities, and abilities try to extrapolate beyond your test set. Even you change the difficulty of your items, you're going to be able to predict how well this model is going to behave for a new distribution of items. The more abilities you have, maybe you can have more predictive power, but of course you need more information in terms of domain knowledge and also data in order to infer all of these new parameters. The number of parameters increases. So what is the challenge to do all of these things? People might think these days that just uploading your code, your data, and the seed that was in the talk, the best paper award, that some people don't. You go there, you don't find the seed, and you cannot replicate the results exactly. But the problem here, especially today with large language models, it takes a lot of effort to replicate this. Even if you are given the code, sometimes you're not even given code. You cannot run all of these millions of examples yourself. So for all the approaches we have been discussing today, and especially IRT, you want to apply IRT to large language models, and especially some other models that require a lot of compute, please share your test results at the instance level. Don't think that just by uploading the code that's enough, because that forces some other people to run this code, and that takes a lot of tokens or compute, and just running the code again, it's a little bit stupid when you only want to do a meta-analysis of the results. That's what we're doing here, just some kind of meta-analysis of the results at the instance level. So that's a kind of a call for, and just all of these extensions, all of them go in the same direction, and IRT goes in that direction. Aggregating performance is okay, but especially when we're going in models that are more powerful, more general, that's very limited in terms of the insight that we can have, and in terms especially in extrapolation to new distributions. I'm going to leave here. Here you have some plugs in terms of the tutorial. There's also an AI evaluation digest if you are interested, where we cover what is happening every month in terms of AI evaluation, not only NLP, but mostly NLP these days because language models are everywhere. Yeah, and questions?
We have a few more slides to wrap up, but does anybody have any questions before we do that?
Practical question. So in the earlier sessions, we went over PyIRT, we tried it ourselves, and we experimented with this. You had then went through a number of more advanced models. To what extent are these advanced models also on PyIRT, or should we also read the papers to find other code to find running these more advanced models?
So I'm not sure I got that one.
Basically, you've shown in this sort of latter portion more models, and my question was, if we want to reproduce or try this out ourselves, should we go to PyIRT or should we go to these papers that you've mentioned in the?
Yeah, okay. There's some code in R in some cases. In some cases, for instance, some of these beta models, they are in Python, that different libraries. My recommendation would be, especially because we try to build a community as well, is that you understand what these, and some of these models are not that complicated. So just take the formulas and try to see if you can implement them, because you have a lot of facilities and you can compare with the base results in IRT. That's something that there's so many things. A different thing is, for instance, this. You want this, there's a package and there's a tutorial. You have to go through this tutorial, but this is maybe more like the other extreme. Here you need to put a lot of domain knowledge, for instance, to build something like you see on the right. But you have the libraries and everything to do that. There's a tutorial, you can go through that tutorial. But some other areas, for instance, some of these things, you need to go sometimes to old R libraries, and maybe it's not ideal. And it's maybe you can have a look and say, okay, can I do that in PyIRT or extend PyIRT? That would be my recommendation.
One thing to note there, pull requests are very welcome for PyIRT. So if you are ambitious and want to take a stab at implementing any of those, we're happy to review that code and plug it in. Any other questions?
Okay, so I think now it's closing remarks. John?
All right, well,
thanks everybody so much for sticking with us through this. Hopefully you've found it informative, learned a bit about IRT, learned a bit about PyIRT, of course, in terms of implementing it in Python, but also just how much more there is to do, right? We've kind of scratched the surface with regards to IRT and NLP, and there's just so much that can be built on top of it. So we're really excited about being able to present this to you and kind of build this community of folks who are looking at this kind of instance level evaluation, both with IRT, but then also as it extends and moves in, past its typical boundaries, let's say. So just to conclude, right, we kind of learned a bit about IRT models and how to implement them with PyIRT, how to use PyIRT, how to extend PyIRT if you want, to implement new models, as well as some examples, right, with the annotation error, training, evaluation, just how once you learn those parameters, they can be plugged in to improve your task, across different types of tasks and different types of use cases. But the big takeaway, right, classic IRT is the starting point. We've kind of shown a proof of concept in some of the stuff we've published and some of the stuff we presented today, but there's a lot of open work and a lot of interesting directions moving forward, and also a lot of stuff that, even just between when we proposed this tutorial and today, that is already starting to come out to show more examples of this in action. So in terms of future directions, right, we were talking in the last section about LLMs. How does this apply when you might be limited in terms of annotation cost or, training constraints? You might not have the resources to rerun inference on a new model. How do we incorporate multidimensional IRT, looking at big benchmarks where you're covering a lot of different abilities, right, in a multidimensional way? Maybe it doesn't make sense to collapse them all into a single data parameter. So you want to be careful about that. And then, of course, predictability. Like once we learn these things, we want to be able to use them to predict performance, predict difficulty for new examples, new models. So these are all kind of subset of areas we think are going to be important moving forward. In terms of some recent work, we just want to highlight, late breaking stuff that we want to just draw your attention to. You can dig into those papers. This was actually just put on archive this week, maybe. Some recent work that is IRT inspired, let's say, looking at human AI complementarity for question answering. And in particular, they do, an interesting thing around multidimensional skill, multidimensional difficulty via BERT embeddings. So they're going to use BERT embeddings to kind of upstream learn a little bit more about multidimensional ability, difficulty, and the details are in the paper for the system they propose, but really interesting work that's worth checking out. Also, some other related work that's recent. We've got some work from 2022 around a different kind of way of thinking about data set difficulty, as well as some IRT work in recommender systems. So different area, but you can kind of see how it's branching out a little bit and see how it's being applied in other areas of work for inspiration, or just to see kind of complementarities and things like that. Just for these slides, we've got a few references, but as we mentioned a couple of times, there's a structured reference list on the tutorial website, broken down by the different sections. We had some pointers for some introductory materials to IRT, some pointers to some of the papers we discussed in detail in the different domains. So we'd encourage you to take a look. It's a growing area. And of course, if you have work you're working on or any references that you would like to share, the website, we can update it with a kind of, living list that people can keep up to date and make sure that, we're aware of the growth in the community and aware of the updates as people are kind of working on this. So possibly most importantly, if you want to continue this conversation beyond the tutorial, the QR code goes to a Google form. So if you want to put in your contact information, we're just going to see, what the response is like, maybe send out set up a Google group, or just kind of send out a digest of updates. If we do update the reference list, we just want to, share information, share updates to PyIRT or things like that. So we'd encourage you to fill that out so we can get a sense of, how we can share this information with others moving forward, beyond this session here. Right, I don't see any phones up, so I'm going to go to the next slide. And then lastly, we just want to acknowledge some of the folks who were very informative in developing all this stuff. We three of us up here, Zhao in New York, so the four of us presenting, but there's a lot of other folks who we wanted to acknowledge, and they're listed here, and there's obviously more that we've probably missed their pictures of, but thanks to everybody who's been working with us on this as well. All right, and that concludes the tutorial. So again, just thank you so much for your attention. More details on the website. And if you have questions beyond today, let us know. We're happy to answer any emails and talk future work or ideas you have, whether it's about the PyIRT package, IRT code generally, or anything around this kind of instance level implementation and evaluation. So for all of us, just thank you again. Thanks. Four minutes early.
There's no lunch today though.
Oh. That's not our fault. That's somebody else's fault. Thanks, Joe.
All right. Bye, everybody. Bye, Joe.
No lunch, yeah, so we're on our own, yeah. We'll have to scrounge, yeah. Oh, good, I'm so glad to hear that, yeah. Yeah.
No, I'm not that. I did the, I was I think. You have the slides online, it's like basically there's on that computer, there's a, yes, there is someone walking around, but if you have the slides like on the website or something, you can just open it. Yeah. I think they want you to use their.
Yeah, so I'm definitely, I will send my computer by email address.
Yeah, or like if you want to log in on the laptop, but yeah, our stuff was just on the website, we could just go to the URL. Yeah. So in the human sense, well, yeah, so basically like knowledge population is like model. Yeah, it's like a score of you say zero, you're not I got that's the first the number of ability of one of the items. So I have like different very low value, very high value. Yeah, one of the misaligned. Yeah, it's not possible to integrate that in here. I think so. In the package, I don't think we have a model that's pretty together. That's actually not that hard. Okay. Yeah. But the basically what you do is modify the insurance. Right, exactly. Right, that populational, they were talking about to the end, it's critical, whatever. The interpretation and like the next should put your response based on this. So this is we right. There's this guessing parameter, and there's a parameter for distance. Right. It's not that constant, it could be inferred. Okay. But the you think Mike and Mike it doesn't make sense. Because I like the size. Like if I assume every answer is I think that this is what it's captured. Because the guessing parameter, let's say you're taking where you start again, you would think it's right. What if I don't know if it's the first answer. And for some reason, the first answer is all, you can also control like how fine grained you can have like -2 and 2. Well, the guess is parameters would effectively be more than maybe you don't need right. So that's part of one of the reasons why you leave this floating value learn. Okay, go back and verify. Yes, exactly. The guessing parameters is accurate. Yeah. I think in our case there's actually no orders, so that's all supposed to be mitigated, but yeah, okay. Yeah, I mean, not always. Yeah, I would try. Yeah, I mean, I could also just try like letting it be inferred and then check manually. Yeah, that's what I mean. Yeah, I think that makes sense. And if it doesn't match, then maybe. Yeah, right. And the second question, that's maybe more like hard for me to grasp, like on the modeling side, we have like singular, or we have like a pact that's represented then in three different forms, like using the templates, and the templates are shared across multiple, not all of them, but some. So they depends across like, I may have like 30 items, but
like pairs of three have the same track, and then 10 of them always have the same template. I didn't imagine that there's like some. I mean, it's not. Yeah, I think there's.
Good look at it. One, they're not independent, but like many examples are independent. I was expecting the model, it'll work. And where the things that break down is there's like, for example, if the difference in item difficulty represents a certain score probability, that breaking that assumption affects that probability, but if you look at the parameters, it probably would. Practically fine. Okay. But the other. The other thing I think is of interest is that the IRT model has a hierarchical model. So if you could incorporate the knowledge that you have into the hierarchical model, right? That you know that you have, say, 3 templates and you draw those templates for that and draw. Incorporate that as part of the generative process as well.
That makes a lot of sense, but I think it will be complicated for
Yeah.
It's more, yeah. It's open ended.
Yeah, I don't know if you know much about topical. It's a very common thing. I have this data, a good example is there's a particular topic model in the huge. Okay. So in this case, your model. Right, and you model tax bill on the thing, but yeah. Whatever things that might probably affect other given politician, so you incorporate that generative process. Senators might themselves having speeches. Yeah. So then you have that pass, and you can have a generative story that incorporates how you think. Political leaning affects how they talk. The observable thing, which is also affects. Yeah. So in general, like verbatim model. Yeah. Information. How it's structured, the IRP stuff is the simple like. We assume that you draw your difficulty from a standard normal, and that not standard normal. Parameters. Story.
Can take any complexity.
Yeah, I think I'm counting data to the max and critical models. Yeah, you're trying to basically fit a model to data. So, yeah, that'd be another way. Yeah. Yeah, I think you like it. Yeah. I don't But yeah, it's
Yeah, I think the lesson from psychology is they spend a lot of they know that we don't have perfect test. It's also one I think they have so imagine just you take all the so some of these examples that we were surprised at. Some of them we don't have an idea.
Well, still hasn't, so exactly right. It's talking about that in control. Right, right, and that's, yeah, it's certainly not the answer. It's more informative than that, I agree with the but there's also work to be addressed for. And just take. We're talking about. The next. Just. Exactly, yeah. Once you get that, like, flip, then you get, it opens up, it's like, well, how are you doing it? Everything went great, yeah, thank you so
Perfect,
much.
no problem, thank you.
How many papers you see out of the distribution? You just go here.